My screen now. So yes, good morning. My name is Sanna Tuomi. I come from VTT Technical Research Center of Finland, and I'm the coordinator in this EU-funded project that is called FlexSNG. And a warm welcome to our first topical workshop that is titled Turning Low-Cost Bio-feedstocks into Valuable Products. And the two products that we are discussing today are biomethane or bio-SNG and biochar. And first, a quick look at the agenda for today. So we will start with a short introduction to the project itself, the project targets, as well as the FlexSNG process, followed by introduction to the two primary outputs of the process, so the biochar and the bio-SNG. Then we have a session on process innovation, starting with a presentation from Creative Optimization regarding the feedstock supply chain optimization. So we are developing these optimization models in order to reduce the feedstock supply costs. Then we have presentations from our two technology suppliers that are involved in the consortium. So we have Sumitomo Forster Wheeler and Wood.
Anna, sorry, we just
Yes.
we just need to change the screen here. 1 second. So
okay, all right.
Just
let me know.
Short interlude.
Yeah.
Okay.
Okay, it works?
Yeah.
Okay. Yeah, so I was talking about Sumitomo and Wood. So Sumitomo will be presenting their fluidized gasification technology, and Wood, on the other hand, will talk about their Vesta methanation technology that that will be applied in the FlexSNG process for converting the syngas into pipeline quality SNG. So then we will break for lunch at 12:30 and come back at 2 p.m. with a session on products and markets. Maria Georgiadou from the European Commission will start by discussing the EU policies that have been set for renewable fuels, and then we will have both external experts as well as project partners presenting the market potential, the future markets, and for the two end products, as well as the market value that we anticipate for both biochar and bio-SNG. Then we will have a short break at 3:50. And the final session for today will start at 4 p.m. It's related to industrial symbiosis and the case studies. So we will be emphasizing the role of industrial symbiosis in the economic viability of biofuel processes. And then we will go quickly through the different case studies that we are now considering in the FlexSNG project. So the case studies will actually analyze the implementation potential of the FlexSNG concept in different target regions, both in Europe and Canada, taking into account the local market conditions. And at the end of this session, we invite you to discuss the FlexSNG process. So we would like to hear your opinions on the strengths and weaknesses on the process based on what you have learned today. Afterwards, we have some time for networking and, I don't know, maybe some refreshments for those of you that are present in the workshop in Karlsruhe. And the event will then close at 6 p.m. So that was the agenda. Then on to a short introduction to the project itself. So FlexSNG, it stands for Flexible Production of Synthetic Natural Gas and Biochar via Gasification of Biomass and Waste Feedstocks. Just a few facts about the project itself. This is a research and innovation action. It's a 3-year project. We started on the 1st of June in 2021. So we are roughly halfway through our project, still roughly one and a half years to go. We received an EU funding of around 4.5 million euros, and we have a quite well-balanced group of partners. So altogether 12 partners that represent 8 countries. We have great coverage from European countries as well as Canada. So this specific call topic was related to international cooperation with Canada. And we were lucky enough to get 2 excellent partners from Canada. So we have Polytechnic Montreal and University of Laval that are really bringing in the Canadian perspective into the project. And their main focus in the project is looking at the profitability of FlexSNG in the Canadian markets. So our ultimate goal in the project is to develop and validate this flexible and cost-effective gasification-based process in order to produce these 3 end products, which are pipeline quality biomethane, high-value biochar, and also renewable heat, using a variety of low-quality biomass residues and biogenic waste feedstocks. So on the feedstock supply side, we're considering different types of feeds as potential for FlexSNG, like woody biomasses, for example, bark or forest residues, agrobiomasses like straw or prunings, and also waste feedstocks like municipal and industrial waste and sludges. And as already mentioned, here are the 3 end products. And of course, we want to maximize the revenue from selling these products. So we're looking at different applications for them. For biomethane, we're considering its use in energy and transport sectors, as well as in industrial use. And for biochar, that can be, of course, used to displace fossil feedstocks in energy production, but we're also looking at soil amendment applications, activated carbon use as construction material, and so forth, depending on the quality of biochar produced, of course. And then, of course, we're in the process, we always produce some surplus heat, and this heat can be used to produce district heating, or it can be supplied as process steam to industrial use. And we have basically 2 focal points in our project. First of all, the feedstock supply side. So we're optimizing the feedstock supply chains. We're using sophisticated modeling tools in order to optimize the overall chain and the logistics of the supply chain in order to reduce the feedstock supply cost by 20%. On the other hand, on the conversion process side of things, we have simplified the gas cleanup process, have some new features in the process itself. So our target is to reduce the capex of the conversion process by 30% compared to what we call the state-of-the-art biomass to SNG concept that is based on steam oxygen blown gasification of biomass and waste feedstocks. And I will be discussing this state-of-the-art concept in a bit. So when taking these together, our ultimate target is to reduce the biomethane production cost by 30% compared to this state-of-the-art case. So of course, at the end of the project, once we have completed the techno-economic assessments, we will know to which extent we have achieved these goals. Then a few words about the state-of-the-art biomass to SNG concept before we talk about the different or the new features that we are bringing to the table in FlexSNG. So the concept itself is, as I already mentioned, it's based on steam oxygen blown fluidized gasification. So this is what it typically looks like. The biomass enters the gasification plant. It usually needs to be still dried before feeding into the gasifier. We're using steam and oxygen as fluidizing gases in the gasifier. The raw gas exits the gasifier and goes to a filter unit where the solid particulates, alkali and heavy metals, and also most of the chlorine species are removed. Then the gas enters the catalytic reformer, where we supply a mixture of steam and oxygen. So we increase the temperature in the reformer to around 850 to 900. And in the presence of catalysts, we convert the tars, benzene, and light hydrocarbons into carbon monoxide and hydrogen. And of course, in this case, we try to minimize methane reforming, as it is the desired end product here. After reforming, we typically have a separate shift reactor where we adjust the hydrogen to carbon monoxide molar ratio of the syngas so that it's suitable for the synthesis step. So in this case, we have the methanation step, so the molar ratio should be at around 3. After shift unit, we cool the gas in a heat exchanger and then further in a water scrubber cooler. The gas exits the cooler at around 40 degrees Celsius. So in this step, most of the syngas moisture is removed. And typically, we inject also some acids into the water scrubber in order to remove ammonia as well. Then we compress the gas to synthesis pressure. And then we have removal of the acid gases, so sulfur species, hydrogen sulfide and carbonyl sulfide, as well as carbon dioxide. So the commercial technologies that are available, the wet scrubbing technologies for acid gas removal, they are typically Rectisol or Selexol. Then in the end, the conditioned syngas goes into the methanation unit to produce high purity biomethane. And as already mentioned, the gasification process requires some pure oxygen, and that is supplied in an air separation unit that is typically in gasification concept based on cryogenic air separation, a kind of a high capex solution for oxygen production. But then if we look at the FlexSNG and what are the new features in comparison to this base case, state-of-the-art base case. So first of all, now that we have the biochar as the other desired product, we actually operate the gasifier at lower temperature. So we already minimize the oxygen demand. So the lower the gasification temperature, the less oxygen we need to supply to gasification. So that is already a benefit. But on the other hand, we are also replacing the cryogenic air separation, the high capex unit, with a new oxygen production technology that is based on oxygen transport membranes. So we are able to produce pure oxygen with lower energy consumption and lower capex than the conventional air separation unit, and it can be integrated with the process, and it can also utilize the heat available in the gasification process. So that brings us some capex reduction already. Then in this case also we can eliminate the shift reaction step. So now that we are applying the Vesta catalytic methanation technology here, it has an integrated sweet shift unit. So it doesn't require a strict control of the hydrogen to carbon monoxide molar ratio in the upstream process, and also the ratio after reforming is already around 2, so it's well suited for methanation. So we can skip this part. Then the capital intensive wet scrubbing process for sulfur removal is replaced with the dry sulfur removal approach. We're using sorbents. At VTT, we have been looking at a combination of activated carbon and zinc oxide sorbents for capturing the sulfur species. And then finally, we get another capex reduction from choosing or selecting the Vesta catalytic methanation. So in the competing methanation technologies, the reaction temperature is controlled in methanation by recycling of gases, which requires investing in recycle compressors. But on the other hand, in the Vesta catalytic methanation unit, the CO2 and water present in the gas actually act as temperature dampers, and therefore the process is a once-through process. No need for gas recycling, no need for recycling compressors, so that reduces the capex. And the carbon dioxide actually is removed after synthesis instead of before. So when all this is combined, the estimated cost savings potential is around 30% compared to this state-of-the-art case. So the FlexSNG process is also based on the idea of having one plant and 2 operation modes. So that's one of the flexibility ideas behind this concept. So the idea is that the plant can switch between these 2 operation modes. It can either co-produce biomethane, biochar, and heat, or then maximize the production of biomethane and heat only. So it can adapt to market conditions and the feedstock availability by switching between these two different operation modes. Let's start off with the co-production mode. So in this case, the target is that is to reach 45% conversion to biomethane. So this is energy basis. So the biomass, 45% of the biomass energy input to the gasification plant would be converted to biomethane product, 25% to biochar, and 10% to usable heat. And in this case, this is achieved by lowering the gasification temperature, supplying some more steam to the gasifier, and we are now restricting the feedstock carbon conversion to gas to around 70 to 80%, and therefore around 20% of the biomass carbon is actually recovered as biochar, and it is extracted from the process as bottom ash or as fly ash. And since we're of course interested in producing good quality biochar, the feedstock base would be something like woody residues or maybe good quality demolition wood, so that the biochar would be suitable for the applications that we are considering here. The other operation mode was the maximized production of biomethane and heat. So in this mode, the target is to reach 70% conversion to biomethane, again, on an energy basis. So from the biomass energy input, 70% goes to the biomethane product, 15% to heat. So in this case, we operate the gasifier at higher temperature, at around 850 to 900, depending on the feedstock. Whereas in the co-production mode, the gasification temperature was around 700 to 800. So we are maximizing the feedstock conversion to syngas in this mode. And one new feature that we have in this production mode is that in order for us to use also these challenging waste and high alkali agro feedstocks, we have the possibility of using the biochar product that we have produced in co-production mode as a co-feed. So in a way, we're upgrading these challenging feeds into more suitable feeds for gasification. What we have seen in the past project is that biochar co-feeding actually inhibits ash sintering, which is a critical issue with high alkali feedstocks. And it also suppresses the formation of tars in the gasifier. So now that the tar loading is reduced, the filtration and reforming of the gases becomes more simple in this case. So in this production mode, the feedstock base could be different types of biomass residues, agro residues, as well as waste feedstocks. This is actually my final slide. I would just like to emphasize that really at the heart of this project, we have the technology development and experimental work. We have already executed a series of pilot test campaigns where we have really optimized the operation conditions in the gasifier, so that we are able to produce good quality biochar alongside good quality syngas. And that is something that will continue, and the project will culminate to validation test campaigns. So a series of week-long test campaigns where the whole process will, from biomass gasification up to final gas cleaning, will be validated in this pilot scale unit at VTT. So we are really focusing on the key enabling FlexSNG technologies, gasification, gas cleaning, except for the methanation section that will not be a part of our validation runs. And also we are testing the oxygen transport membrane module. So we'll be installing it in the slipstream of the plant, so that we can simulate the idea of supplying oxygen to reforming with these new membranes. And of course, as I said, we have a wide feedstock basis, so we will also be validating the process with different types of feedstocks. so woody feedstock as well as agrobiomasses and wastes. And this is really the test platform that we will be using in the validation test campaign. So it's a pressurized fluidized bed gasification pilot, and we have it at VTT in Espoo, Finland. And on the right, we have a picture of this pressurized gasifier. And of course, this experimental work is critical. It serves as a basis for the techno-economic assessments, and later on form the basis also for the case studies that we will be discussing later on today. But that was a short introduction to the project and the process. Emma, I'm not sure, do we have time for questions at this point, or how should...
Yeah, there's one question for you. It's quite a long question on the question and answers box. Now I'm going to have an issue because I have to stand here to read it, but I can't read it without my glasses. Yeah, of course. What is the input feed capacity of the mentioned TRL5 large-scale prototype and output biochar yield? Now that's a biochar question, so that would be for Stephan.
But I guess this refers to the pilot scale unit that we're using. So to get an idea of the mass flow, so the fuel feed rate into the to gasification would be something like 100 kilograms per hour, and roughly 20% of that would be our target to produce biochar in co-production mode.
Okay, great. And there's another question. So what is the innovation content of the TRL by FlexSNG versus the very large number of known gasification solutions on the market?
I think the innovation comes from the idea that the co-production mode, the idea of producing biochar on the site, and how to operate the gasifier so that it can produce good quality biochars. This is something that we have been looking at in this project, and this is something that that is at least to my knowledge is not done in anywhere in commercial scale. So
great, excellent. And the last one here is there regulatory compliance and TRL5 authority permitting documentation developed, including REACH or EU notified body conformity assessment and audit?
I'm not sure.
I think he's just asking about regulatory compliance and permitting, about
related to the experimental work, or
yes, yeah, related to the demonstration plant.
Of course, we go by with the regulations. I'm not sure what is really the point in this question. I'm sorry.
Okay. No problem. Yeah, no, it's not that obvious. Okay, great. There is one more, but we should. Hold on. What about? He says, I wonder about if there is a way of cleaning between changing feedstock. For instance, what about impurities accumulated in the system when you change the production mode? So how do you deal with the changing?
Accumulation of impurities, it's mostly maybe related to the sorbents, but that we use. I don't see that as a challenge, so I don't think that we need to have any kind of cleaning procedures in between changing from one mode to another. So the sorbent beds will be dimensioned so that it can handle varying loads of impurities.
Okay, good. Excellent. Well, I've just seen the time and we're already running behind.
Yeah,
so,
I'm sorry.
No, it's not your fault. I'm just going to say to the people asking more questions that we'll get back to you, that we can either write you an answer or maybe come back to them at the end of Stephen's talk, or perhaps another time. So I'd just like to introduce our next speaker now, Stephan, who's going to talk to us about the biochar aspect in the FlexSNG. I'll just thank you very much again, Sanna.
Thank you.
That's sharing my screen again now. Oh. We have a problem.
It's okay. Don't touch. It was okay.
Oh, no.
No, it's okay, Emma.
Yeah, but this online, they see this one.
We see the PowerPoint.
We need to make this one like that one. They need to be the same. Oh,
I think they yeah.
no.
It's in Zoom,
Yes, because
so then you have to stop sharing.
exactly, that's what I was thinking. This. Stop the presentation. And
Swap display, thank you. The other one?
But it's probably last time. It's nice.
For the online guests, whilst
Now swap, please.
Okay, but it's what? That would be the problem.
It's okay online.
no, but Ernesto, here is the sharing. We can see the notes. Display section.
Sorry.
Just a short delay for the online guests, but we'll be with you shortly. I'll take this opportunity to say to you, if you have questions to ask, please write them in the question and answers box and not the chat box. I don't know if you can hear.
Yeah, but I think they're gonna have to go there. No, you know what? Sorry. I will just duplicate the screen.
I can share from my side if you want. Or you can do it from your own laptop, Emma.
Why we have this problem? On
So we
site,
need
they will
to-
still have. Oh, no, what's wrong? Please. Because they will have to.
You should share the entire screen or go to read mode,
How about
That's what we need. Good.
not
Sure.
just PowerPoint.
I share the screen. Oh, I will share this one in this case.
Now, if you go on PowerPoint and then read mode, not presentation mode, it's the icon on the left of the projector icon.
Is it okay?
Not online. We see the desktop online.
Let's see, let me share this one. The same, but no, it's not the second thing.
But please just
Jump on the one.
Okay.
We are surprised. Okay, now we can share on this screen. Okay. And now. So we will do the yeah.
This way is okay online.
Okay. Not in the meeting room, but now we duplicate. Yes. Is it still okay online?
Yes.
It's okay. Oh. Look.
Yay, okay.
Okay.
I won't touch
Sorry.
anything. Short interlude. Thank you.
Okay, then after this little trouble, my name is Stephan Seidelt from the European Institute of Energy Research, and a warm welcome to everybody here in the room and online. And I have the honor to explain biochar as a product from the FlexSNG project. So the idea, what we can do with the biochar beside its regasification or mixing with a low-cost biomass for the energetic use. So first, what is biochar in general? Biochar is defined as carbonized biomass obtained from sustainable sources and sequestered in soils to sustainably enhance the agricultural and environmental value under present and future management. This definition is taken from the International Biochar Initiative. And yeah, in the scientific or in the public media, biochar is often used synonymous with charcoal and many other biochars, for example, black carbon, pyrogenic carbon, activated carbon, torrefied biomass. It's also mixed with hydrochar. That's another process. Hydrochar is produced via hydrothermal carbonization or liquefaction, the solid product, compared to pyrolytic carbonaceous material coming from pyrolysis or gasification. HTC coal or hydrochar and wet charcoal are also synonyms for the same, and sometimes you also find the word ash for biochar. That's mainly the solid outcome of combustion or gasification unit with a higher amount of carbon. So for us in FlexSNG, biochar is the charcoal leaving, or the solid rich carbon material leaving the gasifier, either as bottom ash or fly ash at the bottom of the gasifier, or after the solid removal of the gasifier. So we are separating both ashes, and we had analyzed both, but it's not fitting to the scientific definition, because the difference between biochar and charcoal is not the production process, it's more the intended use of the solid carbon material. Charcoal is mainly used for energetic uses, and biochar is really dedicated as a soil amendment for other material uses. That's the main difference. So don't be messed up with the whole wording. For us today, or in the consortium, biochar is really the carbon material produced from the gasifier. So beside the energetic use of the biochar, there are many other options where biochar is at the moment considered or already used. It's, for example, as additive for the for animal fodder to improve the microbiological digestion inside the animals. That's, by the way, in Europe, roughly 80% of the current produced biochar is used as animal fodder. Another, but the main remaining part of biochar is used for co-composting, and that's then really biochar in its real sense, because it's used to improve soils and agricultural behavior. That's also soil amendment, similar process. It's used sometimes as additive for biogas plants, because on the solid carbon material, the microbes in the digester have increased surface area where they can better grow and they have more room. Biochar is also considered as a construction material. It can be mixed with cement or in cement, replace some sand, and biochar has some good qualities. Biochar itself has a bad thermal behavior, so it's a good isolating material. And in France, for example, there is at the moment a discussion to reduce the CO2 footprint of new buildings. And if the biochar is used for the construction material, then you can get some CO2 credits. And the overall CO2 footprint of new buildings is reduced. Biochar or many other solid carbon materials are quite good absorption materials for impurities, for example, for water purification or also for gases. It's also investigated at the moment that bioorganic carbon is used for fuel cell, for batteries, for superconductors. Of course, one crucial point is the replacement of fossil coke for the steel industry, because the steel industry has also a need for reducing CO2 emissions. And like fossil carbon materials, biochar can also be a part in the composite materials for organics, for plastics, etc., to reinforce the mechanical stability. So why we are looking at biochar at the moment, what we see here on the left top, there is a huge increase in the scientific literature about biochar. In the last decade, it was a quite nearly exponential growing interest. But as well in industry, as I mentioned, biochar is already produced and used. And just some rough figures, the global biochar market volume is estimated to be around $3 billion. And it was more or less starting in the States. There is a big business. That's, by the way, why the biochar topic came to IFA. And also the production capacities and the production amount is continuously increasing in Europe, what's on the right side, at the bottom. So one quite controversial topic is biochar for agricultural. There was in the last decade a lot of discussions if biochar has positive effects on for agricultural and for the plants or not. And meanwhile, a lot of studies and meta-studies have confirmed that in general there is a positive effect. But the qualitative and quantitative effects depend highly on the characteristics of the soil. For example, it's often discussed that the water retention capacity of biochar biochar improves the water retention capacity of soils. That's, of course, just the case for sandy soils. But on the other side, for clay soils, it has a complete different effect, because then the water can easier pass these soil fractions. So it's really depending on the soil as well as for the plants. And it's also depending on the nutrients. There are some studies that are emphasizing that with fossil produced fertilizers, the effect is less positive than with organic fertilizers. And of course, it's depending on the biochar characteristics itself. On the right side, I have just a recent meta study of meta studies, and it's obvious that biochar has a positive effect. So I think this discussion is nearly at the end, even if there are a lot of open questions, how the interaction between soil, biochar, and the plants is really working, and what are the real effects, and in particular, the reasons behind. So another big interest on biochar was coming since 2019, because it was the first time that the IPC has mentioned biochar as a negative emission technology. If you compare it with the costs and the potentials with other famous negative emission technologies like direct air captures, bioenergy, carbon capture and storage, enhanced weathering, biochar is a very cheap solution, and it's ready for market or for implementation, compared to others where still some development and activities have to be done. On the other side, biochar has a limited potential, because in a sustainable way, biochar or biomass should not produce and then restored in the soil. It's just an add-on to the conventional growth of plants. The good thing on biochar as a negative emission technology is that we have some positive side effects. During the biochar production, there's also in parallel the production of bioenergy. The water demand is comparably low, because the plants are already used and have grown. As mentioned before, the plant growth is improved. The nutrient recovery that's usually lost if you burn the biomass only, you are entering in a circular, in a circle of the nutrient way. And also the main issue for agricultural, the nitrogen emissions are reduced if biochar is implemented in the soil. On the other side, like every new technology or like every technology, there are some potential risks. So on the one hand, the land use, the more biomass is converted or is going to the biochar production, it's replacing other plants or crops that would need to feed the world population. The capacity of soils or the biochar amount that can be stored in the soils is limited. At a certain point, on just carbon, nothing is growing. And a topic that we want to investigate at IFA in the next year is the availability of the carbon. It's nonsense if the carbon is released again as CO2 by natural degradation in a very short way. That's, by the way, issue with hydrochar or HTC coal. It's more labeled due to the production conditions than the biochar produced during pyrolysis at higher temperatures or gasification. So the biochar's properties depend, as I mentioned, mainly on the process condition. That's, of course, the temperature. The higher the temperature, the more stable the biochar is, because it's more pure carbon, and the functional organic hydroxyl or ketone aldehyde groups are reduced. And it's also depending on the feedstock. Independent about the temperature, if you don't burn it, you will somehow find the feedstock characteristics in your biochar. The key characteristics of biochar are, or the main important things is, if we consider as a carbon dioxide removal technology, it's the fixed carbon content. As I mentioned, the carbon should stay in the soil and not be released in several years or decades to the atmosphere again. And depending on the feedstock characteristics and the production process, that the content of impurities and pollutants are, of course, a critical parameter. If you have too many heavy metals or polyaromatics on the biochar, it's not useful to put it into the soil. Even if there are some discussions how the polyaromatics on the biochar are really a danger for the plant growth, because polyaromatics are sticking very good to the biochar or the carbon material. That's why it's used as a sorbent material. And the question is how much and how fast they are released to the plants. That's an ongoing discussion, but you will not find an answer in this project. Some other characteristics are more depending on the intended use of the biochar. That's the surface area and the pore characteristics, if we consider it as adsorbent material, the water holding capacity for its soil use, as well as the cation exchange capacity, the pH value. There are basic and acid soils, and of course, with adding the biochar with a certain pH value, this value can be increased or neutralized. The particle size distribution is also an interesting characteristic depending on the use, as well as the electrical conductivity. On the right side, you see some analysis of the biochar produced during FlexSNG, and as expected, we have a quite high carbon content because we have high temperatures. And it's quite interesting that we are able within FlexSNG to produce char with a quite low content of polyaromatics. So the crucial parameter for us at the beginning was 6 milligrams per kilogram, because depending on voluntary characteristics and voluntary regulation for biochar market, it should be lower. Meanwhile, it's a bit changed, so there are several classes for biochar depending on the characteristics and the intended use, but it is possible to produce biochar with low polyaromatics. And what I already mentioned, there are several markets for biochar. That's the agricultural, the construction, and what we also were checking was activated biochar. And depending on the characteristics, the regulations, the possible feedstocks, and the maturity level, and we try to figure out what could be an interesting market for the biochar in FlexSNG, beside the energetic use. And what we are thinking at the moment, that our biochar is well suited as construction material. There are some, as mentioned before, some ongoing activities on this. It's also a good soil amendment for animal feed. We don't think it's a good market or a good business opportunity. And for activated biochar, compared to the fossil analogs, our specific surface area is too low. So we would need some adjustments by chemical pretreatment to improve the specific surface. On the other side, it's a better absorption material than the typical biochars coming from pyrolysis. So that's it at the moment from my side. Any questions? I don't see the.
Thank you, Stephen. Let's just have a look at the questions we have here. Anything new? Okay, so there's one from Edwards at the bottom there. So, biochar characteristics. Why not the EU FR 2019 109 CMC 14 is applies for characterizations? Is the EU member states PAH regulations considered? That is some cases is 1 kilogram per kg PAH 19. I'm sorry, this is very specific.
Yes, very specific question. To sum it up or to simplify it a bit for the broader audience, it's a mix between the European regulation. Meanwhile, biochar is accepted as a fertilizer in the European regulation. On the other side, there are still the national regulations that has also be respected. That's a complex topic. And I hope that in the next 1 to 3 years, there will be a harmonization. At the moment, the voluntary European Biochar Initiative certificate is based on the strict Swiss regulation. And it's really depending on the intended use of the biochar. If you go for soil amendment, then of course all fertilizer regulations have to be accepted. For construction material, it's a bit different. There you have other regulations because at the end, the regulation for construction material or the final product has to fill these regulations. And for some others, like adsorption material or as activated carbon, there are no regulation in a sense like for the 3 others. That's really depending on the quality and on the industrial requirements. I hope that's a bit clearer now.
So maybe there's just one more question. It says voluntary biochar certificates does not have legal effect only the EU after July 16. You know anything about biochar?
Yes, that's why I mentioned it's voluntary. The legal or the legislatures have to be respected, and that's depending on the country. Each country has still his own. It's more, these voluntary certificates are more qualitative standard, so to harmonize it, because there are many different biochars, as I explained at the beginning. There are many different production processes. Pyrolysis processes are numerous, and each production process has its own characteristics, produce its own biochar, and then if you combine it with the manifold biomass feedstocks, then it's clear there is no one biochar. There are dozens, hundreds of different biochars. And the idea of this voluntary certificate is to harmonize it a bit. That's there, it's a marketable product. But anyway, in each country, the legislative has to be respected.
Okay, I think that's it for the questions online. Has anyone any questions? Oh, you have a question in the audience.
Oh.
Wow.
Sorry, I was inviting to ask a question to the audience. No, just maybe very simple. Are you able to tune the process in a way that you reduce the aromatics in biochar, or is it the other way around that you have to use a certain composition of biomass to have a sufficient low aromatics?
Okay, that's more a question for Sanna or for Ilka or the gasification. The polyaromatics are produced during gasification. And of course, the goal of gasification is to minimize it. But because they make trouble and you are losing carbon for your intended process at the end. There are several ideas to reduce the formation of polyaromatics. At the end, a certain amount of aromatics will be produced during gasification. That's unavoidable. And the question is, in parallel, they are in contact with the biochar. And according to our results at the moment, the contact time or the polyaromatics are not condensing on the biochar because of the special gasification process. For example, if you have pure oxygen, the polyaromatics are easier to destroy. That's depending on the oxygen and the temperature and this stuff. But that's really more on the gasification process. I think you can ask Ilka later or in the break. He has much more experience on the gasification process itself.
Okay, thank you. We are again running behind, so we'll don't forget to ask questions throughout online or in person, but let's carry on with the presentations now. So we've got Erik here from Creative Optimization. Thank you, Stephan. That was really good. We will go on to, let's try to share the screen again. Should be smooth and easy. This problem again.
Let's remove the presentation mode. So I don't need.
Where's that?
Not yet shared on Zoom.
No.
Sorry, Emma, we don't see on Zoom the screen sharing. Try it from Zoom first. Okay, now reading mode. It is right, left side.
Oh, wait. Where am I? This one?
No, just before this one.
Okay.
Okay.
There we go. Thank you, Erik.
Perfect. Thank you. I thought I'll do it in the view. I pushed my camera on the other one, so I'll be a bit more engaging with you in the audience and online, because I realize that it's going to be tricky for me to turn around all the time. I imagine the difficulty. Thank you for having me here. Thank you for all the people who are in the audience and online. Just a very short introductory. We're going to talk about supply chain optimization. And it's sort of, we're going to go into the depth of understanding what is the complexity within the FlexSNG project and what are we doing through the optimization? What are we really modeling? What are we looking at through feedstock to gasification? And I'm not the expert, so I will not talk about the gasification. That's someone else. So our expertise is really looking at feedstock to production. So we are a company called Creative Optimization. We specialize in optimization, so that's our core business. We're really trying to find ways to model reality and really finding the optimal way on a different level, from operative to tactical to strategical level. And in this project in FlexSNG, we are using our current platform called Woodflow. I'm going to go a bit in more depth of what we're doing with Woodflow in this project and what we're developing further to really showcase and include everything within the feedstock delivery. So very quickly going through what are the challenges within this type of optimization and modeling from feedstock in the supply chain. So we need to really understand what are the boundaries here, where are we starting and where are we finishing, what are we including in terms of time frame, what time periods. And we also need to include in this project more about co-development. So how can we co-handle assortments? How can we collaborate with each other to lower the efficiency, well, higher the efficiency and lowering the cost for the overall feedstock to do the promises as told in the project. And for this, we're doing in a modeling approach. And by saying modeling approach, we're trying to reimagine all the activities and all of the processes within the supply chain. So we have feedstock, and then we have all of the process oriented with changing that feedstock. So for example, we have forest residue converted into chips, converted in then later to drying, and then so we can follow the quality over time within the supply chain. And then one other challenge before I go into the feedstock themselves, it's more how do we handle such a geographical differences, because there is a geographical differences from Sweden to Finland down to Corsica down to Italy and then over to Canada. So there's a difficulty in finding ways of handling all of these geographical differences. So just describing the supply chain, we've seen it through the colors and the presentations before as well. We can see that we have the agro-flow, which is more of straw and more agro-waste type of feedstock. We have the forest residues. We have, for example, ships from industry, and we have forest residue from harvesting within the forest itself. And then we have municipality waste, and that could be solid waste wood, it can be municipality solid waste and others, which is included within this project. And trying to produce biomethane, biochar, and heat. So we're really trying to solve this complex riddle. When should we pick one feedstock over the other? How can we mix them? And how can we provide the best results for the gasifier at a low cost? So this is our overall problem. So then we can look at them individually. So we can look at agro waste, for example, and then we realize, what are the challenges here? Well, we have seasonal availability because there's no agro waste during winter and spring. So we have a seasonal availability, which we need to take into account in this project. We have variation properties, energy content, which is very different from straw to prunings from vineyards or olive trees. So there's an handling of the energy efficiency here as well, added on the seasonal availability. Then we have the mode of transport, because there's different types of attributes to handle within this supply chain. So we need to handle different modes of transport as well within this value chain. Then we have price efficiency, because we need to compete with, is it efficient for someone to sell this product for us? And is it efficient for us to handle it in terms of handling costs, drying costs, and then transportation costs to make it an efficient feedstock within the supply chain? And then we have moisture level, because moisture level we need to handle because there's a drying perspective in this as well. We can do it at a dryer, or we can leave it to dry in some ways natural, but we need to take all of this into account when we do agro waste. Then we have forest residues. And then we have the question of, where should we do the processes? Where should we ship it? Because now we have forest residues in one form that we need to convert into ships later on to the gasifier. So when should we do that? Should we do it at the harvesting site? Should we do it at a terminal? Should we do it at the industry and the gasifier itself? The same question here, we need to take into account transportation mode, quality, because there's a difference in quality depending on where we are. There's a resource allocation problem here as well, because now we need to ship it, but we need to also take into account, when can we ship it? Is there a sharing of resource? Since the energy demand is especially in Scandinavia, the energy demand is pretty high during winter, which means there's going to be a competitive challenge in handling, when can we have the resources to be price efficient to produce this for the gasifier. Price efficiency, I mentioned that. And then we have inventory utilization, because handling forest residues and ships, we do have a structure where we can use terminals and inventory to handle this kind of problem in facing shortage of stock or handling price variance, which we've all experienced in these trying times with gas going up, producing the higher price for forest residues as well. Lastly, we have municipality solid waste. It's the same question here. When should we process it? Should we process it at the terminal or where we have all of the solid waste, or should we process it at our gasifier? The availability, is it available all the time? Is there a seasonal variance in municipality behavior? So do we, as people, throw more trash during winter, or is it more during summer, or is it the same? Is this the same quality? And then we have inventory limitations, because now we have sort of a demand for it, but do we have the space to handle it? And then we have the cost efficiency question, because now this is something that others also want, especially in Scandinavia. We have a market where energy plants also want this product. So they also want to compete with this. And in building sector, they always also want to have this. So now we try to find a cost efficient way of when to buy, when to have and handle for the gasifier. And then, of course, as you can imagine, with municipality solid waste, it's a question of quality as well, because we do have some bad and worse qualities handling this impurities. And then we have the limitations on the gasifier itself. So we need to handle campaigns in a good way. We need to be able to switch between campaigns. How long should they run? How long should they handle in terms of our feedstock supply? How do we coordinate these two together to be cost efficient? We also have what kind of recipes do we actually have for the gasifier? Can we combine 20/80 or is it 70/30? Is there a price variance here which we can handle the cost efficiency even better? And then it's the production capacity as well. We have the drying process, inventory space, and yield for feedstock and seasonal variation. So we have a lot of questions and a lot of challenges we're actually solving through the optimization and modeling in terms of how can we do this and replicate it in a model, and how can we present it in a way that we can showcase the optimum of doing all of these feedstocks and the selection of which feedstock should we take depending on the season, the resource utilization, and the processes needed to handle it at a cost-efficient way. So these are the ones that I mentioned before. It's sort of the highlight of the challenges we have and what we're solving within the project. And then just to add a bit of more complexity in terms of supply chain, because now we have sort of a problem. We have a gasifier, we have perhaps prunings, or we have forest residue around. And then we have a terminal, if that's cost efficient, of course. Otherwise, we would load it on trucks. We have a municipality solid waste station. This one it's probably a bit easier to handle in an optimal or logistics way, because this is more of a, it goes into the terminal, it goes to the gasifier. We can handle that in a pretty easy way. These are the ones closest, so we could possibly handle, these should go to the gasifier with truck. So that's also an easy way of handling, the time difference and handling when should we order it, and they should go to this gasifier in terms of their location in a geographical sense. So the distances handled by the truck. And these one, well, they were cost efficient in my example here to go by train. So now we need to add on top of this, we have to add the resource utilization, because now we need to know, okay, so we have no resource to ship at our industry. So how do we ship? In what order do we ship? So now we need to understand, we need to do the optimization on a more optimal level, operative level, doing, the resource utilization in what order? And we need to take this all into account when we're doing the optimization for the feedstock supply to the industry and the gasifier. And luckily, like I said, mentioned earlier, we don't have to reinvent the wheel. So it's not entirely new. We can use our platform as a basis to do all of these things, handling time periods, handling processes, handling resource utilization in some senses for the variety of price, cost for the feedstocks to make it a more optimum supply chain. And this is sort of a description of how we're doing it. We're maximizing net income. So we're letting the optimization select which feedstock, what processes, at what time, what inventory utilization, what resource utilization should we use to maximize the net income in terms of what do we sell the end product for. So we can use that within the optimization to really determine what's the most optimal and most cost-efficient way of handling feedstock. These are just some examples of how we've done bioenergy handling of terminals and shipping before. And these are the further developments we're looking at now. And it's one tricky question is quality over time, especially within forest residues. Like, how can we see how quality change over time and really determine when is it appropriate to select this to be used in a cost-efficient way, so we have less moisture levels for less drying methods. And then we have the resource sequencing and utilization. We have sort of what I mentioned with the handling of the campaigns and recipes for the gasifier, and also the co-handling of assortments. How can we co-handle agro waste, municipality waste with forest residues? How can we coordinate these with the trucks and the partners that are in this geographical area where we're doing the gasifier project? And that also includes the collaboration part. We're going to go a bit through, I think, further on down the line with the case studies, but we have found, the identified interest feedstock for the case studies. I think we will go into that a bit more in detail, so we go on time schedule. So looking ahead, we're really trying to adapt all of this modeling approach to the case studies and for all of the individual locations, doing all of this supply chain optimization in determining when is the correct feedstock right to use in terms of a cost-efficient way of handling the gasifier. And then we're also taking into account the new inputs for the model as well, of course, as we are only halfway into the project. Trying to find new attribute activities or process performance, handling uncertainties, and also including sort of a scenario analysis in this. What would happen if price effects overall? So what would happen if the price change for straw and the price change for forest residue? What would that affect us in the end for the end price of the gasifier and the end product? That was a short introductory and description of what we're doing in this project and what we're doing as a company as well, creative optimization. If you want to have more information about the details in the modeling language, I'm happy to answer those questions.
Thank you, Erik. We have some questions in the audience.
Yes.
Thank you, Erik. Really interesting. I was just wondering, did you analyze about the decentralization of the industry production? Because the transport costs and the fuel costs will be increasing in the future. Instead of if it's electric, but there's, for example, for municipal solid waste, they have the infrastructure they have will be not easy. I was wondering if you also analyzed to put some gasifiers kind of next to the, for example, municipal waste installations instead of just one centralized plant.
So we have ideas of doing decentralized for the case studies, like if you have it close to a municipality solid waste station, or if you have it nearby a pulp mill, for example, you have a bioproduct stream that you can take into account. So we do have ways of handling that, the decentralized way of handling different kind of feedstock. If that answers your question.
Yeah, the cost effectiveness.
Yeah. Yeah.
There's one question online, but I'm not sure if it's for you or for someone else. It's about the competition between gasification and aerobic digestion for some of the biomasses you consider. That's something that... Yeah.
So there's absolutely, I'm not sure if it's the question, but I'll try to answer it in my perspective. It's, of course, there's a competition for the material, and especially in Sweden, there's a high competition of forest residues that's being used for energy plants and all the other bioproducts now as well, looking forward. So it's really to find when is forest residues a competitive product for us to use within the gasifier. Is it perhaps we buy it during another season, not during winter when there's a higher demand? Could we store it, and can we handle and co-handle that with straw to make a more efficient way of using the gasifier at a competitive level in costs?
Okay, great. So I think
maybe just,
yeah,
just wanted to add based on the question, because the question was competition between anaerobic digestion and gasification. It's not exactly the same feedstock that we will use, because the ones that are easy to digest, we don't really gasify them, and the ones that we gasify are not easy to digest with a biological process. So there is of course some product could be in competition, but for most of them, it will not really be the case.
Okay.
Great. Thank
Perfect.
you.
Thank
Thanks
you.
for that. Thank you, Erik. So now we're going online to our online speaker, Frank Lighthouse, who's representing Sumitomo today. Frank, are you there?
I'm here.
Hello.
Can you hear me?
Hello. Thank you for joining us today. So for your presentation, you'll be able to share your own screen, and we'll just go with that then. Thank you so much. Thanks.
I will try to do that. Let me see. How does it look?
At the moment, we can see all of your slides.
All of the slides. Aha. How can that be? Let me just.
Today,
Sorry about that. I should have.
operating in any part of the world today.
Should I share the entire screen or? Let me put it in presentation mode first, and maybe then it works. I don't know. I'm not so familiar with Zoom. Sorry about that.
That's okay. We're all having problems today.
How about this? How about this?
Yes, now we can see it. That's perfect. Okay, I'll leave the floor to you then. Thanks, Frank.
Okay, thank you. And you confirm that you can hear me properly, so I will just go for it then. So good morning, ladies and gentlemen, to this and welcome to this FlexSNG process innovation session. Greetings from Cambridge in the UK, where I'm located at the moment. My name is Frank Ligthart, and I represent Sumitomo SHI-FW, or SFW in short, where I'm responsible for business development for our so-called waste to value and carbon capture businesses. I'm not personally involved in the FlexSNG project, so I do hope I understood the assignment properly, but I will not focus too much on that, but I thought maybe to give you an introduction into our biomass and waste to X concepts, and then of course also make the link to the FlexSNG project. But maybe first a few words about who we are. So who is Sumitomo SHI-FW? So the SHI in our name stands for Sumitomo Heavy Industries, which is our owner, a large Japanese industrial conglomerate headquartered in Tokyo, who acquired the fluidized bed boiler business from AMEC Foster Wheeler at the time in 2017. And FW in our name stands for Foster Wheeler, which is basically our heritage going back more than 130 years. So what we are doing is we are a technology provider providing energy and environmental technologies. And I guess we are best known as the global market leader in the fluidized bed combustion of solid fuels. And nowadays, of course, mostly focusing on biomass and waste to energy. But we are much more than just combustion or a fluidized bed boiler supplier. Of course, at SFW, we have also recognized that the world is changing and very rapidly. And we want to be part of that energy transition and, of course, also help our customers to decarbonize their businesses. So we have diversified our portfolio. Here you can see the 5 businesses that we today have in our portfolio, running you quickly through. So energy generation is still very much at the core of our business, based on the fluidized bed combustion of solid fuels, mostly, or actually today only, biomass and waste for low carbon heat and power applications. Then carbon capture is nowadays a very important part of our portfolio. We developed a so-called oxy-fuel combustion technology already for more than 15 years. We have developed a calcium looping technology for carbon capture already for more than 10 years. And we are also nowadays acting as an EPC/integrator for third-party post-combustion carbon capture technologies, for example, including the hot potassium carbonate process. Services, of course, is a very important part of our business. We offer a whole range of life cycle solutions for keeping the assets of our customers in good shape with high availability and efficiency. Waste to value, as we call it, topic of today, using our gasification technology to convert solid feedstocks, biomass and waste, into a syngas, which then can be converted into a number of valuable products like gaseous fuels, liquid fuels, and chemicals. And also going forward, it can be utilized for recycling of plastics, so thermal chemical recycling of plastics back into virgin-like plastics. Then energy storage is a very important part of our business, specifically long duration energy storage. We made a large investment in a company called Highview Power that developed a liquid air energy storage technology for storing renewable electricity in liquid air. And when you need it again, you vaporize the liquid air and expand it over a turbine, which then also gives you the possibility to provide similar type of grid stabilization services as any thermal power plant. So that in a nutshell who we are and who we try to be going forward. But now coming back to the topic of today, so a brief introduction of our biomass and waste to X offering for the market. So at SHI-FW, we have recognized that there's a growing need and also a growing demand to replace fossil raw materials, so coal, oil and gas, with lower carbon raw materials like biomass and waste in the production of products like hydrogen, methane, liquid transportation fuels, and methanol. And that's why we developed this waste to value concept based on our gasification technology, in which the bio waste feedstock is gasified, turned into a syngas, which then is cleaned to make it suitable for downstream synthesis into a wide range of end products. And of course, here in this workshop, the focus is on SNG, and this is based on our extensive experience with fluidized bed gasification. We have been working with fluidized bed gasification already for more than 40 years, and during that time we delivered 11 commercial gasifiers for a wide range of biomass and waste streams. Our concept for waste to value is based on this oxy-steam fluidized bed gasification process that was already mentioned earlier, and that was extensively demonstrated in a so-called NSE biofuels demonstration plant that I will introduce a bit more in detail later, and in which the gasification was combined with a Fischer-Tropsch synthesis process for producing liquid fuels from solid biomass feedstocks. And today, based on all that experience, we have the commercial readiness for offering 150 megawatt capacity single line gasifiers for a range of biomass and waste fuels. Yeah, I already mentioned that at SHI-FW we have a long history with fluidized bed gasification, going back more than 40 years to the beginning of the 80s, when we started to deliver biomass gasifiers to pulp mills to replace fossil fuels in lime kiln applications. Then if I can put the pointer on, sorry, that doesn't work. 1 second. And then in the beginning of the 90s, we were involved as the gasification technology provider in a biomass integrated gasification combined cycle demonstration project. In 97, we delivered a gasifier to Lahti Energy in Sweden for a biomass and waste co-firing application in a PC boiler, so converting biomass and waste into a fuel gas, which is then subsequently co-fired in a PC boiler. In 2000, we delivered a gasifier to a company called Corenso for the recovery of energy and aluminium from plastic waste derived from liquid packaging waste. Then in 2002, a gasifier to Electrabel in Belgium, similar to the Lahti gasifier, for the co-firing of biomass in a PC boiler. And then the one that I already mentioned in 2009, the NSE biofuels gasifier, as part of a demonstration project to demonstrate the conversion of solid biomass feedstocks into renewable diesel. And in addition to that, via testing at our commercial reference plants and also at our R&D facilities, we gained a lot of additional experience, for example, in gas cooling, gas filtration, but also in gasification with oxygen enriched air and that kind of thing. So a lot of know-how behind our concept. Then just to put SFW into perspective in terms of what do we supply, what is our part in this value chain that you can see here, from the dry solid fuels via gasification and syngas cleaning to the syngas conversion and the end product. So we are at the core of all of this. So we are a technology provider of what we call the ultra clean syngas island, consisting of the gasification technology and the syngas cleaning technology. And then we also act as an overall plant integrator to give our customers an overall solution. And for that, we partner with technology providers that have the pretreatment technology to convert, or let's say to pretreat the feedstocks, and also upstream the gasifier. And we partner with technology providers that have the syngas conversion technology downstream, the syngas cleaning, to convert the syngas into the desired end products. And if we look at the end products, what we see in the market today, the heat and power applications are basically non-existing. That is not a focus for us so much. It's all about synthetic natural gas and liquid fuels, specifically sustainable aviation fuels and some hydrogen applications. Diving a little bit more in detail, not too much, because I think the process was already more or less described in one of the previous presentations. But here you can see our syngas island concept for biomass to X. So running you through that, we start with a pre-treated feedstock. The feedstock needs to be relatively dry, 15% moisture content, and it also needs to be, of course, reduced in size, so below 50 millimeters. Then we have the atmospheric oxysteam fluidized bed gasifier, turning the biomass into a raw syngas, which is then cooled, filtered to remove the dust, but also the alkali metals. It goes to a catalytic tar reformer to crack the tars into smaller hydrocarbons, CO and hydrogen, further cooling, and then a conventional scrubber to remove the sulfur, ammonia, and chlorine compounds. And then you're basically ending up with a gas that is free of tars, sulfur, ammonia, and chlorine compounds, and can be compressed to the right pressure level that is needed for the downstream synthesis process. So the overall cold gas efficiency of a syngas island like this is about 70%, producing a syngas, like I said, that is clean and that has a hydrogen CO ratio of 1.7. So there may still be a need for a water gas shift before going to the synthesis. And the syngas can be utilized for a range of products. So it can be converted into SNG, hydrogen, methanol, or sustainable aviation fuel, depending on what the customer wants. Then very shortly, a similar concept that we now market for waste to X. Slightly different, but also starting with the atmospheric oxysteam fluidized bed gasifier, but then going to a thermal tar reformer. So instead of utilizing a catalyst, basically cracking the tars at very high temperature, and then the various coolers, a baghouse filter for dedusting the syngas, and again a scrubber for further cleaning, ending up with again syngas that is free of tars and free of sulfur, ammonia, and chlorine compounds. Also here, the cold gas efficiency is around 70%. The hydrogen CO ratio is a bit lower. So again, you probably need to have a water gas shift after that. But also here, the syngas can be converted into the same wide range of end products that that the customers may desire. Then how does this fit into the FlexSNG project, or what is our role? What is our interest as SFW in this project? Of course, like mentioned in the previous presentations, we are very interested in this because you know, there's a big potential to reduce the capex, to improve the efficiency, but also to improve the product flexibility, meaning more products, biomethane, biochar, and heat, depending on the need of the customer, via process optimization. I will not go through these points because these have been discussed, but our role in all of this is that as an industrial partner with commercial gasification experience, we take part in the gasification process modeling activities, in the conceptual design for the gasification part, and also in the techno-economic assessment of the gasification part. And as mentioned in one of the previous presentations, the overall targets, of course, are to reduce the capex with, I think it was mentioned, about 30%, and the overall efficiency to bring that up to above 80%. So that is really what we are, let's say, targeting for in this project, to improve the process that we actually already have by reducing the capex and especially increasing the overall efficiency of the process. Then I thought to end this presentation maybe with a few selected references, just to give you a flavor of the kind of applications in which our gasifiers have been utilized. Not going too much in detail, but starting with this so-called Südkraft Värnamo demonstration project. I will just put off the pointer, sorry. For which which was the world's first complete integrated gasification combined cycle plant utilizing woody biomass as a fuel, located in Värnamo in Sweden, for which Foster Wheeler at the time delivered the gasifier and the syngas cleaning system. So it was a pressurized circulating fluidized bed gasifier, turning biomass into a fuel gas for a gas turbine that was part of a combined cycle system. And this unit was started up in '93, and what that was then subsequently tested for about 10 years, collecting about 8,500 operating hours for the gasification part of the plant and 3,600 operating hours for the complete plant, and testing a wide range of fuels, mostly woody-based biomass fuels, but also straw and RDF were tested. So this plant produced 6 megawatts of electricity and 9 megawatts of district heating. But due to the economics of it, which were not very favorable, unfortunately, it was mothballed in 2002. And yeah, after that, this concept unfortunately was not revived, and we don't see necessarily that there is a future for this going forward. Then a more conventional gasifier. We delivered an air-blown 60 megawatt thermal circulating fluidized bed gasifier to Lahti Energy for co-firing a range of biomass and waste fuels in their coal-fired PC boiler. So turning these fuels into a fuel gas, which then subsequently is co-fired in the main boiler, as you can see here, the CFB gasifier next to a main boiler building. And the fuels that were utilized in this project consisted of relatively clean wood waste and bark, then more contaminated construction waste wood, and very demanding municipal solid waste. So quite a wide range of different biomass and waste fuels, showing the flexibility of the fluidized bed gasifier for different feedstocks. So this was started up in '98, showed very good availability over the first 4 years, and also after that of operation, close to 98%, turning 100,000 tons per year of fuel into fuel gas for coal firing in the boiler. Not anymore in operation for the obvious reason that the coal-fired boiler has been decommissioned as part of the coal phase out that is going on also here in Finland. Still only 2, no worries. A little bit of a special reference showing the versatility of gasification. Here, an air-blown 50 megawatt thermal bubbling fluidized bed gasifier that we delivered to Correnso in Finland as part of their liquid packaging waste recycling plant. So this gasifier is recycling aluminium from liquid packaging waste and recovering the energy from that waste. So the process is such that the liquid packaging waste comes to the mill. Then first the cardboard fibers are recycled from that waste mechanically in a fiber drum, leaving you with basically a plastic waste consisting 90% of a thin plastic foil and 10% of aluminium. So the plastic is gasified in the gasifier, turned into a fuel gas, which is fueling a steam boiler. And the aluminium remains in the metallic form and is then recycled or let's say separated from the fuel gas in a cyclone and then recycled. Then the last but not least, because this is really at the basis of our waste to value concept, the NSE biofuels gasification demonstration plant, for which we delivered the gasifier and the syngas cleaning system on an EPC basis. So this plant was to demonstrate gasification as a route for converting solid biomass feedstocks into liquid fuels, located at the Stora Enso pulp and paper mill in Varkaus in Finland. And we delivered the 12 megawatt CFB gasifier and a 5 megawatt syngas cleaning system as part of that plant. And NSE, which stands for Neste, one of the joint venture partners in NSE Biofuels and SE Stora Enso, they provided the Fischer-Tropsch island to convert the syngas into diesel. And this was started up in 2009, then tested for a period of 3 years, collecting something like 8,500 or even 9,000 operating hours, demonstrated that the process is technically viable, but at that point in time, we are talking about 2011, there was no market for this kind of concept. There were no incentives. So after that, nothing much really happened until perhaps a few years back when there was again an increased interest from the market, and we are seeing a lot of activity at the moment with similar applications. Just to give you a flavor of the kind of R&D work that was done at the time. So the knowledge base at the foundation of our waste to value concept. So a lot of things were tested, including, for example, the oxygen content in the fluidizing gas, the gasification temperature, different types of fuels with different moisture contents and particle sizes, bed materials, construction materials were tested. So a lot of testing was done over 3 years, resulting in a vast body of know-how that we are now utilizing in our commercial waste to value concept. At that time, also the scale up was done. So Foster Wheeler scaled up this process to a 300 megawatt thermal plant, for which we already have the design ready. So to summarize this short introduction, briefly recapping the value points of SHI-FW for biomass waste gasification. So very extensive experience over 40 years from commercial gasifiers, but also from extensive testing at our R&D center and at those commercial plants, and of course from this NSE biofuels demonstration plant, basically demonstrating the whole value chain from the solid feedstock to liquid biofuels via oxy-steam gasification, giving us today the commercial readiness to offer and deliver 150 megawatt capacity single line gasifiers. With that, I would like to thank you very much for your attention. I hope this was interesting, and I can hang around for a number of questions if they popped up, or you can contact me later if they pop up later.
Great, thanks, Frank. We actually have quite a few questions online, but before we go online, I'll just check the floor if anybody. Oh, we have one online, but I think you have to come and ask the question here, or I can try and repeat. If you say it now, yeah, you can see, and then I'll see if Frank can hear. If you can't hear, then I'll repeat what you said.
Is the commercial readiness for the 150 megawatt unit based on the Varacas experience or otherwise?
It's a combination. Of course, this NSE biofuels demonstration plant has been very important, is still very important, like I tried to explain. But we have on our track record 11 commercial gasifiers for different types of fuels. Let's also not forget that we have about 700 commercial fluidized bed combustors out there. Okay, that's not gasification, but of course provides a lot of information related to fuels and the fluidized bed process. So it's a combination of all these things together that provides that commercial readiness.
A short different one, you mentioned 50 millimeters for the feedstock to your island. Would you call that feasible or optimal as feed into the circulating fluidized bed?
Not sure if I understood the question. Is that optimal or is that feasible? What?
Are you saying you want 50 millimeters because you know it works, or do you know that that works best?
Yeah, I mean, it's a fluidized bed is very flexible in terms of fuels, but it does require pre-treatment of the feedstock, meaning basically a certain particle size to you know, you cannot just dump black bags into a fluidized bed gasifier. That just doesn't work. So you need to reduce the size. 50 millimeters seems to be the right size. Whether that's optimal or feasible, it's what we see as the best particle size, which also economically is feasible.
If I may ask Ilkka from VTT, so 50 millimeters, I think it's like the maximum size of the particles. So it's then range of from few millimeters into up to 50. So
yep.
so that's the case. So 50 millimeters is not the optimal. It's a maximum size.
All right. Well, yeah. We provide our customers with some flexibility, I guess. I'm not really expert, like I hope I said in the beginning. So I trust on Ilkka's comment that he knows much better than I do.
Okay, great. Oh, another one from the audience. Yeah. Yes, please.
Is there one of your references running today?
Yeah. So we, I mean, unfortunately, most of these gasifiers are not anymore in operation for various reasons, mostly economic reasons. But this gasifier that was part of the energy biofuels demonstration plant is still in operation, though be it in a different function. So it's a lime kiln gasifier. So it's nowadays an atmospheric air-blown gasifier turning biomass into a fuel gas for the lime kiln at the Varkaus mill of Stora Enso. And then this Corenso gasifier that I mentioned, also that is still in operation. Yeah, so we have 2 gasifiers still in operation. The others are, for economic reasons, all decommissioned.
But the economic situation changed a lot during the last month, so maybe now it will be again interesting.
Yeah, and that's also what we are seeing. There's a lot of activity. I mean, that was already before the invasion to Ukraine, but especially after that, especially SNG application, there's a lot of interest at the moment to utilize biomass and waste streams for sustainable aviation fuel. I would say that is really the most activity that we see, and then a second, synthetic natural gas.
Okay, great. So anything else from the floor? Let's go to a couple online before we go over to Fabio, because I know he's been waiting quite some time now to do his bit. So just one question from online. So from Sarah, she said, what is your pre-treatment technology?
So was that the question for us, for me, or?
Yes, it's for you.
The pre-treatment technology. Yeah, so we do not have pre-treatment technology ourselves. It's commercially available technology. Like I said, the feedstock to the gasifier needs to be relatively dry. So you need to have a dryer, typically a belt dryer. And like I said, you need to have a particle size below 50 millimeters. So you need to have a shredder or similar type of pre-treatment technology. But this is, I mean, I would say very conventional technology that is off the shelf, commercially available.
Okay, great. So there are a few more online there, but I think Frank, you should be able to respond to them, to type the response. Do you have the option there to, or would you just like to quickly respond now? So I'll just the next.
Yep.
I think we're quite running out of time, but just one more. Do you have experience with hydrochar as starting material for your syngas island?
Biochar as a starting point,
yes.
Or?
Hydrochar.
Hydrochar. I need to admit my ignorance. I have never heard about hydrochar. I feel stupid, but I don't know what that is.
No, don't feel stupid. I'm not sure it's there. Stephen, do you know anything about hydro?
It's the solid product of the hydrothermal carbonization process, but itself it's more or less pressure cooking of wet biomass to produce a solid carbon material.
Well, from my answer, you can guess that we don't have that experience. I mean, typically the materials are low cost, of course, and so low grade biomass residues or waste fuels, really. That is what we are seeing. Mostly waste, to be honest, at the moment.
Okay, great. All right, Frank. So thank you so much for that. There's another couple, but I'll send you those, and then perhaps you can type a quick response so that
All right.
Fabio too far behind. And thank you so much for coming and presenting online.
Well, thank you for inviting me and giving me the time. So thank you. Bye-bye.
Okay, take care. Thank you. So now we're over to Milan and we're going to speak to Fabio. So hello, good afternoon.
Hello, good afternoon, everybody.
Hi, how are you?
Very good, very good. How are you?
Yes, excellent. Right. So sorry for the delay, but now the floor is yours. So if you'd like to share your screen with your presentation, or you'd like us to share it, that's okay.
Yes, I was expecting you to share, but otherwise I can show mine. It's exactly the same.
If you have it there, then at least you can be control of.
Let me go to open mine very quickly. Just a second. Okay.
Take your time. There's no rush.
Okay. So let me share the screen.
Perfect.
Very good.
Okay. So if you just like to put that into presentation mode, and then
Sure. It's on the other screen, unfortunately.
And you may click on display settings on top and swap display.
Okay. Perfect. Thank you so much. Thank you so much.
Thank you so much, Fabio. Okay, the floor is yours.
Okay, so in the next few slides, we are going to introduce the Vesta methanation technology with more specific focus on the syngas upgrading application of stream biogasification. In this slide, you can already see our pilot plant in China, which has been operated. We will tell something more later on for about 5,000 hours in 2013, 2014. Generally speaking, I believe all the audience is pretty much acquainted on the bio-SNG advantages, but of course, this is a suitable plug-in application for all the existing biomethane infrastructure because it can achieve absolutely the same composition and quality as all the major transportation grids. So it can be used for residential heating, transportation, and any other application. The system is based on all, I can say, much of technology. Everything is commercially available for the methanation. So this is a fully commercial technology suitable for the production of renewable natural gas, or let me say circular natural gas starting from waste gasification as well. Generally speaking, the system is suitable for a syngas derived for a number of different composition and is suitable for a number of end products. Basically, we can start from syngas from wastes or plastics, municipal solid waste, RDF, biomass. It can be used for a biogas upgrading, so to convert the CO2, which is present in a biogas or in a methane, let me say, rich gas with a significant amount of CO2 to be upgraded to a fully suitable for natural injection methane. Or it can even be used with the same topology we are going to show for the upgrading of CO2, so for CO2 methanation. Of course, also hybrid contests where you can, for example, convert the CO2, which is always in excess from waste or biomass gasification. You can convert, once hydrogen from renewable sources available, this CO2 to an additional flow of methane. So this is something that can be easily introduced in the system and can be used to uptake the peaks of production of hydrogen, while where hydrogen will not be available, there will be a production of CO2 that can be stored and collected. For the end product, of course, the main product will be methane, but as we know, as we see that the network are changing and there is an additional fraction of hydrogen which is allowed or required by the legislation, the system with the same topology, so with the system we can design today, is suitable for producing a methane hydrogen mix of a pretty variable nature. Just for an example, we are now completing feed a plant in UK, where we are start to produce methane in the first, let me say, years, because the grid in UK allow only 0.1% of nitrogen in the mixture, with the possibility to upgrade in the next 5 to 7 years the methane from 0 hydrogen to basically 20% hydrogen, and with a minor modification, the system from here to 10 years will be suitable to produce pure hydrogen. So with the same basically system, we are going to follow up, let me say, the energy transition, adapting the system for this kind of variation in the demand of the product. Coming a little bit more specifically to our methanation, the main peculiarity of our methanation is that it's a one-screw operation, so there is no recycle compressor required for the control of the system. The system uses the CO2, which is already present in the syngas from the gasification, and a very small injection of water to control the extent of the reaction, so to control the thermal extent of the reaction, but also this will act as a sort of chemical flywheel, allowing us to accepting a very variable quality in the syngas gasification without, let me say, the need to have any adjustment done by the operator. So the system will automatically follow up any variation from the syngas quality upstream. So these make the system very, very easy to control. We can design the system up to a very, very large scale. This figure is 250,000 cubic meters per hour, which is definitely not the case for biomass system, but the system was conceived back to the early 2000s as a system also to be used downstream coal gasification, so for the very large scale, but now, of course, the main application are definitely on the renewable or circular economy application. The catalyst is a very, very high stable catalyst, very well referenced also already in industrial application in the US. It can operate in a pretty wide range. Here is reported 230, 700, but we tested even a wider range, so from slightly above 200 up to 720, and the system was very, very stable with a very good conversion in the wool range. The system is, the catalyst is suitable for both CO and CO2 methanation at virtually any ratio among these two compounds. It's very, very robust in terms of carbon deposition towards the test we have performed on a very, very enriched CO system with very low steam, and is a very standard catalyst based basically on nickel metal, so there is no precious metal involved in the system. We reference to the advantages that the system has towards a stoichiometric technology, so the one that needs to have a recycled compressor for the operation, or isothermal technology that need to have a very complex reactor to be managed in terms of the thermal. We do have, as a general rule, a roughly 20% less capex, and the system, mainly because of the lower power consumption associated with the recycled compressor, can have around 15% lower energy consumption compared to the competitive technologies. The system is operated at equilibrium, so there is no active machinery that keep the composition in order to avoid the loss of the thermal control. So there are no runaway intrinsically possible for this system, and this is due basically to the presence of the CO2, the water, that act as a thermal and chemical damper for the system. In terms of additional benefit for the technology, generally speaking, we have some non-exclusive partnership with the main well-established gasification sensor. Of course, we have a very, very good relation with Sumitomo Foster Wheeler, which was basically part of the Foster Wheeler back to, let me say, not so many years ago, back to 2015. So we have a very, very good relation in place. We can deliver a full modular system, so a standalone solution that can take the syngas, the raw syngas basically from the gasification up to the network injection, depending of course of the characteristics of the syngas that need to be evaluated on a case-by-case basis. The system, of course, results in a system that is very easy to transport. And we can go now to a few slides relevant to the references. So this is our demo plant in Swindon. It is based on biomass and waste gasification. The system is almost ready to go online. We face some delays, basically due to financial situation of the company that now has been solved. Now it is in the hot commission, so we are expecting to start up in the next, let me say, couple of months. In our scope, there was the modular delivery of the full final gas cleanup, the methanation, of course, as well as the CO2 removal, the drying of the SNG, but also here is not reported the liquefaction and the upgrading of the CO2. Our section is, as I mentioned, they are fully completed. We are waiting basically for the startup. Then here is an example that has been developed on the basis of the Sumitomo gasification technology back to 10 years ago. So the figure you can see on the right are maybe a little bit old. They need to be adjusted a little bit, but this was a case fully developed for a 200 megawatt hour SNG production, so roughly 300 megawatt of biomass input, so 21,000 to 22,000 normal millimeter per hour of SNG. The configuration was based on, as I mentioned, on a CFB gasifier oxygen blown with a catalytic reforming from VTT at the time was integrated. The best solution was resulted to be this one. This was a study that has, let me say, look at a number of potential solutions, and this was the most promising one. The system in terms of the H2S removal in this case was based on a physical solvent for specific reason, mainly associated to the size. The methanation was the vested methanation technology, while there was a simple chemical washing for the CO2 removal. As you can see on the right, there are a few figures in terms of efficiency and cost that can be updated, of course, if the client has a current business case with a biomass cost. These are a little bit now outdated. As another potential application that we have already mentioned, we go very, very briefly, we can upgrade the CO2, which is present in a methane rich, in this case was a biogas, so we can, with a renewable hydrogen source, upgrade from electrolysis, basically. We can upgrade the biogas. Instead of having only the CO2 removal, we can convert all the CO2 in the biogas to an additional production of methane. So this is a pretty much advanced renewable gas production integration. The same system, the same concept is applicable to a pure CO2 stream. We start to see in several areas of the world significant interest also for this application, especially, of course, where there are abundant availability of renewable sources. Not really so much in Europe, for example, but this is another application that start to see a significant incentivization scheme, especially in the US. So it's something that we are really looking at as well. Here is a wrap up of the main characteristic. I think we have already basically went through all the system, but what I would like to add is that in this moment, as mentioned also from the previous speaker, there is a very deep interest in terms of the SNG production. We have a number of ongoing base design packages, fixed price quotation undergoing on several, on very, very different scales, from 15 to more than 100 megawatt in different areas of the world. In Europe, we have a couple of, Europe including also UK, we have a couple of BDP undergoing, and another couple, they are in the US, Canada region. So it's a really, really, there is a very momentum in this moment for the SNG. And we are delivering basically a couple of packages per week, supporting the client in better understanding the applicability of the technology to various solutions. I believe that this was basically all. Thank you so much.
Thank you, Fabio. We've actually got quite a lot of questions for you.
Very good.
Hang around just for 5 minutes to answer the question. So we'll start with the floor. So, Mary, you have.
It's a colleague who is using my connection information who wanted to ask a question.
Oh, okay. Okay, so I'll
to register, sorry.
I was confused why you were writing to me, but that's okay. I'll read it out loud, the question to you. So the first question, will it work with the syngas coming from different gasifiers, fluidized, downdraft, updraft?
We have already developed, let me say, paradigms for all these kind of gasifiers. So basically, all these type of gasifiers are perfectly generating a suite of a syngas which is perfectly suitable for the methanation. Of course, there are different pretreatment sections involved. There are different yields depending on the temperature of the gasifier and other aspect, but the system can be absolutely tailored to all these kind of system. There is also a question on the capacity just below this one. I believe, yes. Well, again, virtually, we do not have any particular restriction in terms of the feasibility because the system is based only on fixed bed axial reactors, so there is no real lower limitation. At the moment, we believe that to have a sustainable full chain, a system at least of 10 megawatts start to be something sustainable. But if you have already let me say, the gasification available, you need to test. We have designed a system of 2 megawatts, 1 megawatt, and that are perfectly viable. Not for the whole, let me say, system integration. I believe that 10 megawatts, maybe even better, 20 are a scale that start to, let me say, pay for itself on the basis of the typical incentives we see around.
Okay, great. And there's just another one here. What is the conversion efficiency of Vesta?
Oh, the conversion, we are going, but this is true for all the methanation technology. We are going with more than 99.9% conversion. So virtually is full conversion. There is no residual nothing other than the methane residual in the system.
Great, excellent. And anyone in the room? Any questions for Fabio? Yes, Ilka, please.
Yes, so Ilka, hi. It's the inert content in the inlet of the Vesta.
This is a very, very important point. This is true for basically all the methanation. It's not something which is technologically peculiar of the Vesta, but is something associated to the methanation. Why? Because the methanation happens with a very strong mole contraction. So the molar flow that you have at the inlet in terms of nitrogen, argon, or any other inert will be found at the outlet. This means that if you have 1% in terms of fraction at the inlet, being the reaction happen with a strong mole contraction, almost 4.5 to 1, you are going to have 4.55% of nitrogen in the final methane. And these need to be reviewed in terms of the network specification. So in the Netherlands, there is quite flexibility, so you can accept a decent level of nitrogen. In other part of the world, for example, in several specifications from the US, the total inert limit, including the CO2, is in the range of 4%, and so you need to limit the total inert upstream below 1% if you want to achieve this figure. Or there are technology that we know we can integrate in the system to basically reduce the nitrogen content, but this comes with a significant capex and a very significant loss in terms of the calorific content of the system. So if possible, it's always best to operate on the content in the single substrate.
Thanks.
Okay.
You're welcome.
There's just one more if you have time.
No, I do have 10 minutes more. I can.
Okay. This is online. It's quite long. There's many questions in one, so I'll just try to start. When you say deep desulfurization and dehalogenation, what is the maximum content at the methanation reactor?
Well, the methanation, basically, let me say, virtually, the methanation, we are pretty close to zero. We are in the terms of 0.1 ppm for both the halogens and the sulfur. But there are, on the other side, no limitation on what we can take upstream because we are capable to design a system which cope with the different composition. We have designed a system for more than 1,000 ppm HCl content, for example, and we do have design for more than 1,000 ppm sulfur at the inlet. Of course, this will be removed with different technology depending on the content, size, and conditions.
Okay, great. So then there's another one, the same, it says from the same person. Does desulfurization mean hydrogen sulfide or are organic sulfur compounds also a concern?
It's all the sulfur should be removed. So basically it's relevant to the total sulfur regardless the chemical composition.
Okay, then another one. Last are tar and light hydrocarbons, C2 plus, also an issue. What purity is required?
Well, generally speaking, our technology is very, very flexible for the peculiar, let me say, characteristic of both the catalyst and the operation. So we can accept a very, very wide range of components. Virtually in terms of C2, C3, C4, there are no limitations. Then, of course, they will not be present in gasification, but we never face any, we never saw the limit, let me say. So there are no limitations in these terms. In terms of the TAR, if you are discussing about BTX, we can design the system. Of course, we are changing some characteristic of the operation up to basically 5,000–6,000 ppm of BTX without any problem, changing a little bit the condition. Ideally, the cheapest solution with the best efficiency will be where the BTX can fall below 300 ppm. So below 300 ppm is a very, very simple system. Otherwise, we need to, let me say, adjust, but nothing dramatic, but adjust a little bit the system in order to cope with this higher level. While for the higher tar, phenanthrene, anthracene, the real tar, let me say the class 4 or higher, or other, sorry, we need to have a deep removal. So basically below 10, 20, no, 10 maybe is a little bit too tight. Let me say 30 milligrams per noble cubic meter, it should be removed upstream. But it's not particularly difficult to remove the higher tar. The critical one are the BTX, and on the BTX we are very, very flexible in these terms.
Okay, great. Well, that's all the questions from online. I'll just open the floor again if there's anyone. Any more questions? Otherwise, I think that's it for us. Thank you so much, Fabio.
Thank you so much. Have a great day. Bye-bye.
Okay, bye then. Bye. Okay, so everybody, for our guests here, we're going to break now for lunch. For our guests online, we will also be breaking for lunch, but I'm afraid there's no sandwiches for you. So we will resume at 2 p.m. sharp, and enjoy your break, everyone. Thank you. So welcome back. Now being recorded. Welcome back, everyone, and welcome back online. Hope you had a nice lunch break. And so now, this afternoon, we're going to be starting with Ilka from VTT, who's the project coordinator, is going to be introducing the FlexSNG project and market session. So I'll just hand over to Ilka now. Thank you very much.
So thank you very much, and nice to be here.
I'm not sharing the screen.
Okay, let's wait for a minute. But yeah, welcome on my behalf also here, and especially for those who have now joining this meeting. So basically now before noon, we looked more for the process. What is the concept? What kind of technologies we have for fuel handling, for the biomass and waste gasification in the syngas, and then the methanation section. During this afternoon session, we feel like go out of this box. So in a way, the box which we have in this project. So of course, now when thinking about the markets and the products, this is much energy, and as we speak about the energy, and especially renewable energy, and then also bioenergy. So so then it's all quite much politics linked into it. And we know the current situation in Europe also. We don't globally, we have climate crisis, which then there is much policy about how to lower the CO2 emissions. At the same time, now we have an energy crisis ongoing. So how we find the sources for power, for heating, for gas. So this is of course bringing from the policy side, pushing towards these kind of processes and bringing them into the market. But then at the same time, of course, there in the policy, there are also things which are, well, bit like the obstacles also to bringing new technologies into the market. And fortunately, we have now here today one really good guest speaker from European Commission, and Maria Georgiadou will then present more on these aspects. Then the other drivers which are there are of course the markets. Markets for the both products which we produce, synthetic natural gas and biochar. And also especially in the case of biochar, also the applications are really in an important role. So which are the valuable where these kind of quantities can be used, and then from the bio-SNG side is then also the specifications, which then apply also in the biochar case. So that was shortly introducing this session, and next we go into our guest speakers and the presentations, and enjoy.
Thank you. Thank you, Ilkka. That was a lovely introduction. Did anyone have any questions for Ilkka before he runs away? It's okay, you can run.
yeah, you may ask from me.
But also later there will be a discussion session and networking. So if you do think of something for Ilkka, you can ask him then.
Yes.
Okay, so now we go over to Brussels, where we have Maria Georgiadou, and she's going to give us an overview of the policy in Europe. So thank you, Maria. Can you hear us?
I can hear you very well. Can you hear me?
Yes, we can perfectly. Thank you.
Okay, I would like to share the screen now to give you the presentation. First of all, I would like to say a big hello to everybody and a good start to this project, which is one of the most actually contributes to one of the most important areas these days under the policy for the renewable fuels in Brussels. With this, I will, I guess you can see.
Not yet. Yeah, now you can see the screen.
Okay. We can see the whole thing?
Yes, yes, you can.
Okay, I will lower my screen so you will not have this black spot here. Is it okay?
It's perfect.
All right.
Great. Okay. Without problems today.
All right. Okay. So my name is Maria Georgiadou. I am a senior expert in the area of renewable energies and renewable fuels research and innovation policies. And I work in the European Commission in the Directorate General for Research and Innovation. And today I will give you a small, let's say, overview of what are the EU policies for the renewable fuels. The overarching policy is the European Green Deal. And the European Green Deal is a way of transforming actually all the EU economy for a sustainable future by intervening to all the economic sectors, from the mobility to the industry, to the energy production, to the agricultural and food industry, also to mobility, and with actually protecting the environment from the pollution and for the diversity and for the climate, and financing the transition without leaving anyone behind. And here is the way we implement the Green Deal, which is called the Fit for 55 package. This is a package of 15 interrelated proposals, legislative, which are either new or amended of existing legislative proposals, and they are applicable to the energy, to the climate, to the transport, and to the taxation and trade, the general areas of legislation in the EU. And here I have put some of the, let's say, more applicable for the renewable fuels. The important thing is that most of this legislation foresee reductions on the greenhouse gas savings. And this is exactly what is done through the effort sharing regulation or the emissions trading system, or even in the land use, land change and forestry regulation and the Fuel EU Maritime. So there, with the use of renewable fuels, these legislative proposals ask, including, of course, the use of renewable fuels, not only, ask to reduce the greenhouse gas emissions from these sectors to which they apply. On the other hand, there are also specific targets for biofuels, advanced biofuels, and biogases, which are included in the RED directive, and we will see these are the old ones. We will see how these are renewed under the REPowerEU, and the renewable fuel EU for aviation. These targets are for sustainable aviation fuels for 2030 and 2050. It is important to understand that also the taxation directive, the one which is now discussed in the trilogue, proposes reductions for renewable electricity, renewable fuels, advanced biofuels, advanced bioliquids, biogases, and biomass fuels. On the top of this Green Deal and Flex and Fit for 55 legislative proposals, we have lately the REPowerEU plan, which is actually the plan of the EU to reply to the energy crisis that was created also by the war in Ukraine. And this has three pillars. The first pillar is on the energy savings. There, the proposal is to increase the energy efficiency target from 9 to 13%. The second pillar is about diversifying the energy supplies. This means that either with a platform, an energy platform in which countries join to have common purchases of gas, LNG, and hydrogen, or extending the engagement with suppliers outside the normal and regular suppliers in order to secure gas and LNG deliveries. And the third pillar is the one that actually pushes to accelerate the renewable energy technologies, and there it is proposed to increase from 40 to 45% the rest target in the RED directive. And this means that there should be massive scaling up and speeding up of renewable energy in power generation, in industry, in buildings, and in transport. Along with this comes the solar strategy with a rooftop initiative and the heat pumps, a double rate of deployment, and the speed up of permitting of the renewable projects for power generation. Also, the hydrogen accelerator for production infrastructure and storage, in which we have a target of 10 million tons domestic production and 10 million tons imports to replace the natural gas, coal, and oil, with delegated acts for the definition and production of hydrogen, with extra funds and important common European interest projects. Very important and central in this is the biomethane action plan. This plan has a target to double the EU biomethane production from 17 now to 35 billion cubic meters per year by 2030. And this will happen through an alliance with the industry and through financial incentives to increase the production, also in collaboration with a common agricultural policy and with research and innovation to support the innovative technologies. And of course, it is about decarbonizing the industry with renewable hydrogen and electrification, research and innovation for material circularity, solar flagship, hydrogen valleys, etc. If we look a little bit closer to the biomethane action plan, which was announced earlier this year. So this plan is about, has also 5 big groups of action. One is about the sustainable production and use of biogas and biomethane. And there we foresee the partnership with the industry to promote the production and the use. Another is through the national policies to set national strategies for biomethane, or integrate them in the national energy and climate plans of the countries, broadening the scope of the fuel supply obligation in the RED directive, to engage multi-stakeholders, to speed up the permitting of the technologies, and to cooperate with neighbor and enlargement countries, for example, Ukraine. Now there's another group for incentives for the upgrading of biogas into biomethane in order to reduce the cost for the economic operators. Another group of actions looks at the infrastructures. Is there any need of a regional assessment for network development? What are the infrastructure challenges and what are the standardization needs? A big group is on research and innovation needs, and there is to support the production of biomethane through innovative technologies, but also the upgrading of biogas to biomethane through innovative technologies, to have solutions for overcoming the barriers to the market and to integrate the biomethane to the gas grid and provide access to the gas grid, and also to expand the feedstock through the sustainable biomass from resources that are not yet included into the production, like from industrial wastewaters, from municipal solid waste, from municipal wastewaters, using algae technology, from marginal lands, contaminated lands, etc. And of course, all this through providing access to grants, loans, other financing instruments like the Innovation Fund or the EU Investment EU. Research and innovation is going to complement and to support all the actions that I have already presented at the REPower EU, with a special focus, since we are now talking about biomethane, to doubling the ambition for biomethane for the 35 billion cubic meters per year by 2030, and supporting all innovative technologies that are needed to boost the production at this level. We use funding programs in order to support the renewable fuels and all the other technologies, of course. So this depends on the technology readiness level and the commercial readiness level. We start at low technology readiness levels with Horizon Europe and LIFE. And then as the technological readiness level increases, we have instruments like Innovation Fund to support first-of-a-kind projects and plans at low commercial readiness level, or when this increases, we have the Connected Europe facility, and finally for pre-commercial projects, the InvestEU and the EIB with debt financing. The strategy for the renewable fuels is under Cluster 5 for the climate, energy and mobility, with the destination sustainable, secure and competitive energy supply, which is one of the strategic orientations and the impact that we want to achieve by supporting secure, competitive energy supply. And there, under this, we have fostering the European global leadership in this type of energies. And there, where the renewable fuel technologies and the renewable energy technologies in general are funded and supported, because they provide unique solutions to long-term decarbonize the transport, but also the energy-intensive industrial sectors. In this view, we support from early stage disruptive technologies up to improving the performance and reducing the cost of existing technologies, or de-risking them by upscaling them into a pre-commercial environment, integrate them better in energy consuming sectors, enhancing their sustainability and supporting their market uptake, and also through international cooperation to reinforce the European scientific basis and the European technology export potential. So here you have an overview of what we have supported for renewable fuels in 21-22 work programs, and on the left-hand side we have all the important topics, including carbon negative biofuel production, meaning here we had a topic where the CO2 emissions or generally greenhouse gas emissions during biofuel production should have been captured and used, and also making products like biochar that would create negative emissions. Also, we had supported the biomethane production for big projects, innovation actions have been in particularly supported in 2022 to contribute to the REPowerEU, and that was not foreseen in terms of budget. The budget was doubled in order to, during the implementation of the call, in order to support REPowerEU. Of course, in other areas, like in the value chains or in the competitive production in existing infrastructures or under renewable energy carriers for heat and electricity, we have covered biogases and biomethane in general under the renewable fuel topics. We have still topics that are open and they close in January 2023. I list them here. Important is to see that we have one on international cooperation, where also a value chain on biomethane or advanced syngas would be included, could be included. Of course, we have algae and RFNBOs, artificial photosynthesis, and gasification and combustion, cleaning of the emissions for industrial use. Here I have listed so far the projects from 2013 under Horizon 2020 and Horizon Europe that have been supported, and there is many projects. There are about 17 projects and cover all types of instruments. And you see here the distribution that we have paid almost 80 million to these projects. Half of the money goes to the innovation actions as expected because they are big projects, and then the other half it is mostly goes to the research innovation actions and then to support measurements for the market uptake, coordination and support actions. And you can see also the projects we have more support actions and then research and innovation and then innovation actions. And then if you want to go to more support, we have the EU Catalyst Partnership under Horizon Europe, which is a topic under the other actions and the indirectly managed actions. And for us is to support innovative green technologies for large scale mainly deployment, and the areas are the clean hydrogen, the direct air capture, the sustainable aviation fuels, and the long duration energy storage. And the Innovation Fund also, this is another fund outside Horizon Europe, which is supported by the ETS, the emissions trading system, the allowances that are produced from the emissions, and low carbon technologies are supported through this fund, mainly large scale, meaning many millions of euros for large pre-commercial plants, like the one that was supported in the first call in Ecoplanta in Spain for the biomethanol. About 100 million euros EU contribution, and the BECS in Stockholm, which is, as it says, in a heat and power combined biomass-based plant. There's also implementation of bioenergy, carbon capture and storage, and that was a contribution of about 180 million EU. So there is a lot more, and I would be glad to answer any questions that you may have. Thank you very much for your attention.
Thank you so much, Maria. That was really interesting. So I'll just open the floor for questions here in the room. Any questions about? Okay, I'll just check online as well for any questions here. No, so for now there's no questions, Maria. But if you'd like, would you like to hold on for and then watch the next presentations in case someone thinks of something, or will you be shooting off?
No, we'll stay connected for this hour, and if there is any question in between, meanwhile, you just let me know, or you write me in the chat, or you let me know. Okay.
Fantastic. Okay, thank you so much again, Maria. That was really, really interesting, and I think the floor as well. We're just a little tired after lunchtime. We had a very heavy German lunch. Okay, thank you. And now, so we're over to Sacha, who's in the UK, and Sacha's joining us from Guidehouse, which is a consultancy firm, and they have written lots of reports about biomass, biofuels, biogas. So now we're going to hear from Sacha. Hello, can you hear me?
Yes, I can, loud and clear. Can you hear me at your end?
Another familiar British accent for the only today. Great. So I will hand over to you then. The floor is yours. If you'd like to share your slides and.
Yeah, let me just do that. Please let me know if you can see the slides.
Yeah, we can see that. Perfect.
Great.
Yes. Okay, we can hear you, we can see you. So
great. Thank you very much, Emma. It's, a nice hello to everyone in the room and everyone online. It seems that I missed out on a very satisfying lunch, so I should have really turned up in person today. Maybe next time. But no, thank you very much for the invitation to speak today. So my name, Sacha Alberici. I'm an associate director at Guidehouse. I've worked extensively on the topic of bioenergy over the past 15 or so years. Recently, I've been closely supporting the Gas for Climate initiative. Gas for Climate really aims to better understand the role that renewable and low carbon gases can contribute in a future energy system. On screen, you can see a few of the recent publications from Gas for Climate. Of most relevance to today is the biomethane production potential study, which was published back in July of this year. And I'm delighted to take you through some of the key findings from this study today, in particular in the context of gasification. Just to say a couple of words, the overall aim of the study was really initiated in the, I guess, in the context of Repower EU and the 35 BCM target for biomethane by 2030 that is set out in the plan. But we also importantly took a longer view on the production potential estimates, looking at 2050 as well. I'll just spend a few moments explaining a little bit about the research scope of the study. So I've already mentioned the time horizon of the study. In terms of the geographical scope, we looked at the EU, as well as 3 additional countries. 2 biomethane production technologies were assessed: anaerobic digestion, which is commercially deployed today already, and thermal gasification, which is fast commercializing. There is, of course, hydrothermal gasification, which is an additional gasification technology that was not explicitly covered within this study because of the potential overlap with some of the feedstocks that might be relevant also for anaerobic digestion. You can see we covered a broad range of feedstocks, primarily wastes and residues, focusing just on thermal gasification. So you can see these are mostly woody biomass type feedstocks. Just to walk through each of these one by one. So firstly, forest residues, which are primary residues which arise from forestry operations, so thin-ins, for example. We also included landscape care wood, which is essentially material that arises from generally in urban areas, from management operations. Municipal solid waste was also included, but this is really the residual waste that is left over beyond recycling. It also explicitly focuses on just the biogenic share of that waste. So that's just an important point to bear in mind for today. 2 additional feedstocks, prunings relating to, for example, management activities in orchards or vineyards. And finally, wood waste. And this is a secondary form of woody biomass that relates to, for example, wood processing industries, also relating to construction and demolition waste and waste wood that might be collected from households or industries. A very important point to mention is that stemwood and also stumps were excluded from the analysis because of potential concerns relating to biodiversity impact and also carbon stock impact. 2 final points to mention on this slide. Clearly, some of the feedstocks can be routed to either technology. So, for example, agri-residues could also be gasified, but we have routed each feedstock to one technology to avoid double counting. We also did not look at renewable methane in the context of this study. Both biomethane production technologies can play a real key role in renewable methane production with the utilization of the biogenic CO2. So to say a few words about the methodology, as you can see, a 3-step approach. Really the emphasis was on step 2, which was to derive feedstock potentials per country in 2030 and 2050. And we did this firstly looking at available literature that covered country level data in the 2030 and 2050 time period. Or otherwise we used statistical data and then extrapolated out to 2030 and 2050. One key study that was very relevant for the gasification feedstocks was the study here you can see from Imperial College London. So we largely utilized the data from this report. A couple of points to mention in terms of the feedstock potentials. These were sustainable potentials, so including, for example, existing uses in the non-energy sectors. We did actually also include or deduct for existing uses in sawmills. There's a lot of wood waste that's already utilized by that sector, so we excluded that from the potential. We also importantly applied sustainable removal rates for forest residues to ensure that soil quality and biodiversity was not impacted. So here we have the outputs for 2030, and you can see for both the EU and the whole of the country analysis what we derive. So 41 billion cubic meters of biomethane for the EU, and you can see this is higher than the target that's set out in Repower EU. In the 2030 time period, overwhelmingly the biomethane potential is based around anaerobic digestion. Nonetheless, there's still a contribution that can be made from thermal gasification. So we estimated around about 3 BCM across Europe with this technology. If we look at the country profile, you can see the potentials range from around about 8 BCM down to almost nothing at the other end. But clearly some countries dominate the potentials, and these largely are due to the size of the agricultural sectors in these countries, be it for livestock or for crop production. If we look at the feedstock mix, I'll focus mostly on gasification, but I think the overriding message is that wastes and residues really are the key feedstock for both the biomethane technologies. If we look at gasification, 75% of the potential is based on woody biomass, of which 60% of that potential relates to forest residues and wood waste. The balance is from municipal solid waste. And just to reiterate, this is just the biogenic share of that residual municipal solid waste. So if you were to include the fossil share, then clearly the potential would be higher than we've derived here. So let's now take a look at 2050. We can see the picture is quite different. In 2050, there is now a meaningful contribution that can be made from thermal gasification. So in total, for all of the countries in scope, we estimated some 165 BCM. Just as a point of reference, before the invasion of Ukraine by Russia, Europe was importing around about 155 BCM. So that just provides a bit of a sense of the scale. Of the potential, 40% relates to thermal gasification. The potential is again dominated by a few countries, but these are broadly similar to 2030, but we see the distribution is slightly different. Also now includes Sweden and Finland in the mix, and this is by virtue of the size of the forestry and wood processing industries in these countries. Looking at the feedstock mix for 2050, beg your pardon. So again, it's quite a similar picture compared to 2030 for gasification, although the share of woody biomass feedstock now increases to 80%, and MSW reduces to 20%. And that is because of the assumptions made in the Imperial report about future potential of MSW, which is forecast to reduce over time. Clearly, there needs to be primary sort of focus on reducing the amount of waste that we produce as society, and also better sort of recycling and utilizing that waste before we start using it for energy. So this final slide, in terms of the analysis, just shows the 2030 and 2050 numbers side by side. Three key messages really: that there is significant potential for biomethane production, both for 2030, but also importantly up to 2050. Gasification can make a meaningful contribution to the potential in 2050, potentially 40% of the total. We see of that potential, 5 countries actually make up around about 50% of the total. Now, these numbers are all well and good, but there needs to be concerted effort really to get anywhere near to these potentials. They're certainly not a given. So on the screen here, there are just 3 potential areas that should be explored to help scale up sustainable biomethane production. The first is mobilizing feedstocks. If we look at wastes and residues, or woody waste and residues specifically, in some countries in Europe, these are systematically collected and utilized, but this is not necessarily the case across Europe. So there needs to be effort to establish supply chains and to start utilizing this material. Clearly, strict sustainability criteria must be applied to avoid unintended consequences. Similarly for MSW, there needs to be more activity to unlock potential here, but certainly not to compromise overall waste management policy aims. There needs to be continued technology innovation, improving gasifier efficiencies, gas quality, the whole methanation process. Also importantly, the technology innovation should focus on ensuring that there's a broad suite of feedstocks that can be utilized by gasification, and also that multiple technologies are being pursued to ensure that the actual sort of opportunity is increased, not by focusing on a more narrow set of materials or technologies. And finally, there needs to be, importantly, investment in commercial scale gasification plants. We've had some good demonstration examples, but there needs to be scale up at large scale. So I think policymakers need to set out really a long-term policy framework to enable this. There needs to be also, importantly, a continued focus on cost reduction for the technology. But industry needs to needs to start investing. But really, they need to have the confidence to do that. But that is really the key for the coming decade, I think, to that we start to see commercial scale facilities being brought on stream. I won't cover the details on this slide, but it's just really a snapshot of some of the support that a few selected countries in Europe provide in relation to biomethane, in particular for gasification. I think it's fair to say that the support is sort of patchy. There needs to be a lot of effort really to, I think, provide more targeted support for biomethane from gasification beyond what is currently being provided by certain countries. So I think there's certainly a lot of promise, but really still a lot more is needed for industry to scale up. So I'll leave it there. Thank you very much for your attention. You can find details of the report on the Gas for Climate website, but I'll be happy to answer any immediate questions that you may have at this time.
Thank you. That was really interesting, different perspectives, because we're all here very academic focused here, and that was a nice outside view. So does anyone from the floor have any questions? Yes. Oh, so many questions. There's a lot of questions for you.
Everyone's woken up after lunch.
Yeah, Ilka raised his hand first, so we'll start with.
Thank you. So maybe from the via the gasification route, there is then different end products possibilities as jet fuel or methanol. So how has that been taken into account in this work?
Yeah, no, absolutely. So clearly producing biomethane is just one of the options from gasification. It's a very versatile technology. I think it's fair to say that there has been a lot of focus on producing SAF from gasification. We see a number of plants in development. For this study, we just assumed the feedstock was being utilized to produce biomethane, but you are absolutely right. There are competing, I guess, uses for that feedstock with using gasification as a technology. But that was not explicitly covered in this study. It purely focused on looking at the feedstock availability and what that would potentially produce if we were to convert that to biomethane.
Thank you.
Thank you. Okay, who's, I think, Stephan?
Just a very simple, short question. Why did you attribute straw and agricultural biomass to anaerobic digestion and not for gasification?
Yeah, so that was a choice that was made in conjunction with the steering committee of the project. So as mentioned earlier, that's one feedstock that can potentially be routed to both technologies. We, as a group, decided to route agri-residues and waste towards anaerobic digestion, being the currently commercially deployed technology. But in reality, absolutely, agri-residues could also be routed to gasification, as could slurries as well, through hydrothermal gasification. I think that's one of the beauties of gasification. It's such a versatile technology, but we took certain decisions in the context of this project.
That's it, it's flexible. FlexSNG. Anyone else in the room? Okay, Erik.
I had a question regarding, you said you removed stumps from
yeah.
forest.
Mm-hmm.
How
how come you remove stumps, and do you have any indication on what that potential would have added if you would have kept it?
Yeah, if I recall, it represented about 10% of the forest residue potential. So I think there's, and maybe Maria can also chime in, but there has been, I guess, a lot of focus at the political level in terms of discussions on revisions, for example, to the Renewable Energy Directive on the use of materials such as stumps because of associated sustainability impacts, but also carbon stock impacts. So if you're removing those stumps from the forest, that can have a significant carbon impact. So I think the policy direction is certainly to not to use those type of woody biomass materials and focus on other materials that could be available. So that was the reason, essentially, to align with European policy. Although I know in some countries the use of stumps can currently be accepted.
We actually had this conversation at dinner last night, actually. Okay, anyone else from the floor? Great, I'll just check online.
Sure. And please do feel free to get in touch post workshop if there are other questions that should arise. Otherwise, thank you very much for your attention.
Thank you.
I look forward to the rest of the presentations.
I have one question. Just
Oh,
quick,
sorry.
Oh, yeah, sure. Okay.
How is this received?
Well, I guess my question to you would be by who? Which audience?
So overall.
Oh.
How about let's do it on political level.
Yeah, I think, to be honest, in terms of the I think the Commission has been referring to this study, so I think it has helped to provide better clarity on the I guess the available potential in the 2030 time period, in particular. It also will be, I think, invaluable for the biomethane industrial partnership, who are now looking to, I guess, accelerate biomethane production in Europe to better understand, which feedstocks are likely to contribute, mostly to that potential. But also, I think member states have found it useful because it gives a frame of reference, particularly for those member states that haven't really looked into this before, more visibility on how much biomethane could be produced within their geography. So I think, yeah, overall, I think good feedback.
Great. Oh, there's some more questions. Sorry, Sacha, I hope you didn't have to run off.
That's okay. No, I'm intending to stay for the whole hour.
Great. Who is next? I think Ilka again. Yeah.
Well, still, yes. One question regarding the maybe now current situation, quite much of those forest biomass potential is going for heating purposes and for electricity production. So was those and currently the electrification is then something which we are targeting on 2050 perspective. So I doubt there will be quite much like a capacity from the biomass side, which is then becoming like for other purposes. Was that any way taken into account?
Yeah, so I think that's right, as you set out. I think also with biomethane, it's a very versatile form of energy. I mean, it can really be applied in any end-use sector, also for heating. So, I mean, I think we see in the 2050 time period certainly a high level of electrification, but in some countries or contexts, there could also be biomethane that's used for heating. But equally, I think it will play a key role in transport, as well as potentially in power production in gas peaking plants. But yeah, I think the overall sort of, I guess, direction of travel is electrification, largely for heating.
Great. How, Maria?
Yeah, it was. I had almost the same question as Ilka, but in addition, I was just thinking in your study, it's really based on potential. You didn't consider the current use of the biomass and availability or the fights that they can have to access this biomass, right?
Yeah. So we did, and I apologize if I didn't make that clear earlier, but we did account for existing non-energy uses. So for example, for straw, that's widely used in the livestock sector. So that was excluded from the potential. We did also specifically exclude also energy uses in the wood processing industry. So there's some 25 million tons that's currently utilized by this industry in Europe. So we deducted that from the potential. But the balance was the balance that's available for bioenergy purposes. So we haven't made, in the context of this study, decisions on how that is used. This study provides a perspective on what would be the potential if that biomass was to be used for biomethane production.
Great. Okay. Well, we're going to move on now. Thank you, Sacha. That was really,
Sure.
really interesting. And if there are any more questions later, I'll send you an email and then we can answer like that. And now, next up is Möller. He's here in person. So I'll share the screen here. And he's going to tell us about biochar from an agricultural perspective. So if you'd like to come and take your place on the magic. Oh, you must stand here. You can use this here, and the floor is yours. Thank you.
Yeah, thank you for the kind introduction. Good afternoon together. My name is Möller. I'm head of the section of agronomy at the LTZ Augustenberg. LTZ is the Institute of Applied Crop Science or Applied Sciences in Agriculture. We do a lot of research on applied agronomy, or my institute on agronomy and on plant nutrition. And simultaneously, I'm professor or lecturer of plant nutrition at the University of Hohenheim. And I was asked to give you a short presentation about the agriculture perspective of the use of biochar under different climatic conditions. I have it's a short presentation. I have some slides on the effects, on the overall effects on the productivity, on the yields of crops, depending on different factors, soil factors, the effect on the phosphorus availability, a slide with a comparison of costs of different approaches to reduce CO2 emissions on agricultural land, and at the end, some conclusions. There are few meta-analyses. There are a lot of publications about or investigations about the effect of biochar or biochar, the different kinds of chars on the on yields and on soils and so on. But at the end, the yield is the integral of the effects, and the yield show are these effects that are very often stated as increased nutrient absorption in the soil, increased water availability, and so on, are relevant for the productivity of crops. And when looking on the worldwide studies, we can find here is the scale of this meta-analysis of minus 50% to plus 100% of the standard without biochar. You can see the main effect is about 10% yield increase across more than 230 pairs of comparison. But looking on different regions of the world or different growing conditions across the world, we can see that under continental and humid temperate conditions, like here in Central Europe, there is no effect. The main effect you can see, and it's even stronger than 10%, is in the tropical and subtropical regions. We know that these soils are very old soils, lasting for 100 million years, and so on. These soils have, are very degraded, we can see that the main effect where a yield increase was achieved is under low soil pH conditions. We know that these very old tropical soils with very high precipitations, this precipitation means that cations are leached out, and this leads to acidification of the soil, and the pH, soil pH of these soils is very often largely below the optimal range, while in nearly neutral soils or soils with a pH in the optimal range, you cannot find a major effect of biochar application. Another statement is that biochar will increase the absorption potential of the soil, the cation exchange capacity of the soils by the high amounts of charges on the surface of this material. And what we can see that it means that in soils with low cation exchange capacity, we will expect a higher effect than on fields with a high cation exchange capacity. And what we can see is no differences depending, or almost no differences depending on different range of cation exchange capacity. What we can see, the main effect is a pH effect. We know that most residues from agriculture, most organic residues have a liming effect. Plants are taken up more cations than anions, and they compensate this with organic acids or the basis of organic acids. They release protons to compensate the higher amounts of cations than anions. And when this material is brought back to the soil, you have the opposite effect. When the basis of organic acids are decomposed in the soil, this means that they will consume protons, and this will have a liming effect. And the same is true for the biochar. And at the end, the same is true also for the ash. When you burn it up to the end, you will have an ash, and the ash has a liming effect of 10 to 50% of a calcium carbonate. Another meta study showed the similar picture. The grade mean was 10% or something like that, and they have here more specifically the pH effects below 5, the strongest effect with plus 40%, pH between 5 and 6 plus 20%, pH higher than 6 to 7, no effect, and in soils with even higher, in alkaline soils, even neutral or slightly negative effect. The latitude, here latitude, tropical, strong effect, in temperate regions, no effect. They differed in feedstock type in the tropics and in temperate. And I don't know exactly what they mean, but also here you see in the tropics a stronger effect than in the temperate regions where you don't have any effect. This is a meta study from myself, carried out several years ago. We compare different recycling options for phosphorus containing feedstocks, and biochar is here. 100% is the effect of triple superphosphate with water-soluble phosphorus fertilizer, and the rock phosphate as an alternative standard is here more or less have a fertilizer efficiency of 30–35%, and the biochar is very similar to a rock phosphate, meaning that very often the phosphorus, and depending on the temperature of the overall process, when you have temperatures above 300 Celsius, this means that the phosphorus compounds in the organic matter is transformed in less reactive forms, meaning a decrease, and the higher meaning a decrease of the reactivity and plant availability, and the higher the temperature, the stronger this effect, the lower the phosphorus availability of the residue after the treatment. Yeah, for another presentations, I compared the CO2 mitigation costs based on the prices you can get biochar and other options to mitigate CO2, and we have two options: either to store CO2 we have the money and we can spend this money to produce, for example, more energy by photovoltaic or wind energy or so on, or we can take this money and store carbon in the soil or wherever. And with the biochar, you have carbon CO2 mitigation costs based on the prices of the biochar you can sell in the market around 1,000 euro per megagram. And with photovoltaic power, this is old prices, not the current prices. With the old prices, it's 5% or something like that of them, meaning that if I have 1,000 euro, it's much more better for the climate to produce more photovoltaic power and to keep, in order to keep more fossil energy there where it is, instead of trying to reduce the CO2 from the atmosphere by this biochar. Another interesting option is the use of mafic and ultramafic stone meals. This is a new approach where the weathering of the stone meals is a CO2 consuming process while having a liming effect in the soil. This is much more cheaper to store CO2 and soils than the biochar approach. Coming to the conclusions, is often very expensive. It depends on the prices of the feedstock or of the remaining product. Very expensive approach to sequester to CO2. We have limited potential of feedstocks in our society or in our system. Another aspect we have during the process is large losses of nitrogen and sulfur, and a reduction of the reactivity and plant availability of phosphorus. We have no relevant advantages under temperate climate conditions. Beside the liming effect, we have to lime our soils as in the tropical regions, but liming is in most of our soils have a pH in the optimal range, meaning that the liming effect of the immediate effect of the liming effect of biochars will not be transformed in yields. And the advantages under tropical conditions seems to be related to the liming effect. There are several references stating this, but this effect can be achieved also by the original feedstock or by the ash when trying to burn this and to get additional energy for whatever we need. And another aspect, many soil properties are depending on the transfer of or on the decomposition of organic matter in the soil, or on the activity of soil microbial on the soil microbial activity. For example, the aggregate stability or the nitrogen mineralization. And biochar is almost a very stable product with a very low decomposition rate, meaning that this effect on soil microbial activity is not further achieved, meaning that maybe the biochar is able to increase aggregate stability on one hand, but lacking of this feedstock will mean a decrease on the other hand. And last but not least, there are some studies indicating that under certain production processes and temperatures, there is a risk of neosynthesis of organic contaminants. Thank you very much.
Thank you. Does anyone have any questions for us? Yes, please.
Thank you very much for the presentation. I was just wondering, because like in my mind, it's kind of contrary about the expensive approach of sequestering CO2, since, for example, the organic fraction of municipal solid waste or like wood residues, so for example, for the cost of feedstock would be kind of covered there, and there's as well low signification, for example, furnaces, no Kentucky Kings, or I guess they're the furnaces. So there's low technology, signification, so to say, to produce biochar as well.
But if you go in the market to buy biochar, you have to pay a lot of money. If a farmer, I took the prices that farmers have to pay for biochar.
Not for the biochar producers.
No.
That's for German biochar, or
yes, a German biochar. We have an experiment where we are comparing this mafic and ultramafic stone meals, a long-term experiment with one treatment of biochar. And for this treatment, we make a market analysis, and the cheapest one was €1.50 per kilogram biochar. And when transforming this in CO2 equivalents, you will end up with something 1,500 euro per megagram CO2.
Okay, only so that was the perspective.
Mm-hmm. It's the farmer's perspective, what they have to pay for biochar.
Yeah, it would be more sense. Make sense, like I don't know, another fertilizer that maybe they nitrogen. Like instead of biochar, I guess.
But we cannot see a fertilizer effect.
You know, it's exactly other things rather.
Yeah, please.
Yeah, I have a question. You compared the fertilizing effect of biochar in comparison to established fertilizers for already established agricultural areas. As far as I understood, no?
This comparison is with and without biochar.
Yes.
Yeah.
But but on established agricultural areas.
Yes.
And it would be interesting for me to know if you investigated an effect of biochar on the humus formation. So when you have desertified areas which are not usable for agriculture, that biochar might be an opportunity to get those areas back to agricultural use.
I don't believe on. I think probably these areas are lacking on soil microbial biomass turnover. And maybe the most promising option, I do not have experience on melioration of this deserts at the end, but probably the effect of several years of cover crop or green manuring will be stronger than a single biochar application and cheaper. Probably. The other aspect is that I stayed for many years in Chile, and Chile in the northern part is desert. And if you have one rain in 10 years, you will have a lot of growth there. It seems that in deserts, not the soil properties are the major problem, but the water availability. And probably even these soils, just if they are not saline, providing with water, you will get a lot of growth there.
In mind, I had more the not desert areas, but areas which are in a climate which could be usable for agriculture, but where the soil is not rich in humus. For example, old what is it, lignite mining fields, where you just use what you got out of the earth and fill them up, and there you see no growth for the first 5 or 10 years or whatever.
I don't know.
Okay.
You have to check it. Or make an experiment of different approaches.
Yeah, I will.
Go ahead.
Yeah,
Yes,
I think it'll prepare.
I'm just a bit curious that where is actually now this biochar then used by the farmers if there is not like effect in this climate and soil in a way? Why they have it?
For 1,500 euros.
If you believe on it,
yeah.
Why many people use personal care products without effect?
Yeah.
Why?
Yeah.
It's what I mentioned. It's organic. It's an organic fertilizer, and more in the Europe or in the States are looking for organic food. And if you then can, it's a marketing effect.
Yeah.
Of course, if you use fossil fertilizer to produce organic food, then that's from an economic point of view, it's somehow reasonable.
You feel better, and maybe this is an economical aspect. You feel better when using some personal care products or by using there are many products in agriculture. There is no proven effect, but they are used, not only biochar. There are many others.
Yeah.
And biodynamic preparates, but also conventional agriculture. The farmers feel better, and this has an economical value. And a very broad view, this has an economical value. Yeah.
What do you think about slow release fertilization with biochar instead of fertilization with a conventional fertilizer? Yes.
It's cheaper to use the slow release fertilizer directly without biochar. And I don't know what the studies are showing, but I would state that it is even more efficient to separate.
Investigations are more focusing the biochar in the light of slow release fertilization, and the studies you showed are more focused on the use of biochar itself.
Yes.
And that's the problem of the results in the past, that biochar wasn't used the way we want to use it in the future. We want to use the biochar in the future as a fertilizer, as a slow release fertilizer, and also as a negative emission technology. It is helpful to use it. Of course, it's expensive, but we need these technologies in addition to all the other technologies to remove CO2 from the atmosphere, to get a climate change from 1.5 degree to 2 degree in 2050.
Let us discuss in 20 or 30 years when we have removed the fossil fuels. it's much more cheaper to reduce the consumption of fossil fuels by producing more photovoltaic or wind energy or what else, renewable energy. And if we are able to remove all our fossil fuels of our system, then we can discuss how to reduce the CO2 in the atmosphere. But starting now, we can spend the money either for photovoltaic or for biochar. And we will have 20 times, around 20 times more effect with the photovoltaic than with the biochar, based on the values 3 years ago or 4 years ago. And in 20 years or 30 years, then we can discuss how to reduce the CO2 in the atmosphere. But our first issue is to stop the consume of fossil fuels. This is the most important target for the next 10, 20 years. And to put all our money in this. This is my personal opinion, to put all our money in the reduction of fossil fuel consumption.
And how is conventional fertilizer produced?
This is easily, biochar will not provide nitrogen. Biochar, the nitrogen is lost by biochar production. This means that you must produce even more nitrogen.
50% of nitrogen is lost.
Completely. You have no, with 300 degrees, you have no further nitrogen effect. But nitrogen or ammonium is probably one of the technologies to store solar power or wind power, or to store as chemical energy, and you can use it either for processes in the industry or to use it in the agriculture as fertilizer. This is a current. Today, nitrogen fertilizers are produced by or by use of gas, but the process of transforming electric power into ammonium is established process. There are some pilot plants in Saudi Arabia and elsewhere. For me,
there are so a lot of positive effects of biochar in the soil we didn't discuss in this presentation.
There are no relevant effects. The yield effect is the integral of effects. And there are no effect on yields. Then it means that all these processes, you are from Offenburg probably, all these effects are not relevant.
Yes.
Are not relevant. They are not relevant.
Okay. Now,
this is the issue.
It's
there's the difference of significant and relevant. You can have in science a significant effect. But it's another question, is this effect at the end relevant?
But this is what I said before. The studies you discussed are from before 2018. So, and the new research, we discussed fertilizer, biochar, where we can improve also the proper productivity.
I don't believe. Okay. I don't know the study. I don't.
This is a very
like this discussion.
Me too.
Shift it to the comic way.
Exactly. Yeah. Very good. Thanks for your help, Stephan. Yeah. Okay. So thank you very much. It was really, really great conversation. Really, yeah. I didn't expect it to rile the crowd so much, but fantastic. We have the networking afterwards that you can continue with, and there's also a discussion section as well. So now actually there's just a slight change in the agenda because David Piemontis is able to join us a bit earlier. So we thought he was going to be joining us at 3:30, but he's here now. So we're going to skip straight to David and then afterwards will be Stephan to round off this session. So David, can you hear us? Can you see us?
Yeah, sure, I can see you. Good afternoon. Can you hear me?
Yes, we can hear you perfectly well. And
Okay, good.
welcome and thank you for joining us today.
You're welcome. So can I share the screen?
Yes, yeah.
Well, let's try. I don't have the option to share screen now. Actually. Yeah, okay, no, sorry, I have it. Yeah.
Sorry, today, David, we all have problems sharing screen.
Okay. Is it okay? Can you see my screen?
You can see it in the small slides. I don't know if you want to make it full screen.
It is full screen. It is full screen in the moment.
Yeah, it's okay like that. Everyone can see. Yeah, it's fine. Okay, so the floor is yours.
Okay, thank you. Well, thanks. Good afternoon. Thanks a lot for inviting me. I will go through some issues, but I'm in quite disagreement with what I heard today in the previous discussion. So I would like to explore a bit some of the arguments that we have addressed, mostly when I will start discussing about the use of biochar in soil. We are currently coordinating a number of European projects on that in very arid land, but I will show this. Let me clarify one point first. We are talking, when it is used in the soil, of an amendment, not a fertilizer. This is not a fertilizer product. It is an amendment product, which brings in other type of considerations. So let's go first of all to have a quick look. That is taken from Ithaca study. I'm sure many of you knows that it goes from animal feed. We have a number of activities that are dealing with this topic, but also char is very much used. It's very sexy in that moment, I would say, in the area of human feed, even pizzas, hamburgers, and so on. It is used in wastewater treatment and some storage of fluid products. This is one I got recently in a box from France. It is used as the secant material instead of a typical gel materials that are there. This is another European project, and BBI we're going not that specific bag, but in the field of littering and other market similar related products. Of course, there are more high-tech uses for the carbon. It's not the same carbon. It is used in painting of rooms, in cosmetics. Is very frequent now. This picture is from very long time ago. Now it is quite common to see charcoal-based products, even toothpaste, for instance. Bricks, floating bricks. That's a funny thing. Indeed, also in other fields, which is not my area of work, but other colleagues here at Polytechnic Torino that works on the electrical properties of some carbon-derived products that are produced in different ways, in different conditions, with different materials, and blah, blah, blah. So we must be aware we're talking about so many different products that it's hardly possible to use a single word. Naming biochar is convenient, it's easy, but we must be aware we're talking about products that can be very much different one to the other. You can tune porosity, you can define surface functional groups in various mean. You can go for very pure, very, very high value product on from very low end. And market size of these products also is very, very different. I will come back to this when we talk about the use in soil. Indeed, anyway, there's a quite high interest in the energy storage area for carbon in that period. There's a lot of researchers, publications ongoing on that. As regards production of the product, we know that we go from very rude, primitive, I would say, sieves, which are kilns, to retorts. It can be even rather large in scale, to converters that are probably the focus of our of our discussion today. I mean, the most likely diffuse technology for that. Indeed, there's also the fast pyrolysis and also the gasification. I will come back to gasification and hydrothermal carbonization in a moment, because I want to focus on pyrolysis, particularly not on fast pyrolysis, but on slow, sometimes intermediate pyrolysis, where the product, the solid product, is the main focus of the business case, also not only on the technology. These systems, I would say, are all mature. Some have been developed a long time ago, apart from kilns, I mean, but also the others are rather dated. I mean, Pyrovac was in the early 2000s, for instance. Coren has left a long time ago. Auger, rotary drums, screw reactors, that's very common, very mature process. The same as retorts, which has also been left aside in many cases and was mostly focused on charcoal making. There are a number of reports from FAO on charcoal making dating back end of 90s. For that, the main goal is to produce the charcoal, as I said, and not really biochar, but can be considered also for our case. Indeed, these traditional methods are very polluting, so we don't want to see this. I think we all agree. And not only because it's polluting, which is a major reason, indeed, but also because it is a loss of efficiency, a loss of resources. All these gases are indeed polluting the environment, but also creating a loss of performance, a loss of efficiency. I mean, but this is the story. Large part of the world still use this system, so we must be aware there's a large room for improvement there. The problem is the cost, and I will come back to this also later, because I heard figures which I don't see in our plans, that scale. I mean, we have a number of plants. We work in that area since mid of 90s. This is the largest plant we have, is a rotary kiln, traditional, I would say, rotary kiln reactor. Is 100 kilogram per hour, 10 tons plant. In terms of weight, is the largest demo we have. But we also have fixed bed reactors like this one that has now been upgraded. I don't have the picture here with me, but it has been industrialized, but it's completely different from the characteristic of a rotary kiln. One is autothermal, this fixed bed, the other is externally fired. We have also paddle reactors or a new type of reactors, which has a compromise of all the previous systems, trying to optimize and recover. And we go for many different applications here. The latest one is the transport of molecules to combat the colon cancer on a carrier of biochar, for instance, which means to tune very carefully the properties and the characteristics of the biochar. Just to say that as Professor Mike Antal from Hawaii University, that passed away years ago, but was one of our pillars in the field, was always say that there's a world of opportunity really in these solid products that can be so variable and so different. So at this moment, we have projects on the steel making industry as well. So we go from conventional systems like rotary kiln to oxidative autothermal systems with all the advantages that they bring in. For instance, the fixed bed and the rotary kiln are comparable size, 50 kilogram per hour, 100 kilogram per hour, but their weight is 1/10 the other, and the cost also is very different. You can move from fixed bed to rotating kiln, screw reactors, paddle reactors, and you can operate in slow and intermediate conditions. That also makes a big difference with many different feedstock. Now, when we talk about carbonaceous products, normally, and also in this project I see, we can refer not only to products that in pyrolyzer comes from very different reactors and materials and process conditions, but even from different thermochemical conversion processes. And typically these are three. pyrolysis, gasification, and hydrothermal carbonization. The products are not the same, and the business cases are not the same. Try to make a quick summary. Again, it's maybe a bit simplified, but I would like to focus on the key elements of these business cases. So slow pyrolysis and hydrothermal carbonization in a certain way, with respect to the policy area and the business model, they are product oriented. Their main goal is to have a product that is competitive in price under the many possible incomes for that product, and they're fully based in the bioeconomy value chain, let's say, which also include bioenergy, but does not focus on bioenergy. Is the cascade use of energy of biomass, for instance, the criteria here. When you move to gasification, we do have a number of gasifiers, also oxidative ones and fixed bed. And we've been working a lot in that area until there were incentives and support for gasification. They were working quite well, but the business model was based on the energy products that you generate. So it's inevitably depending on incentives and the use of heat. This is the other point, which is not of great interest for the Mediterranean areas, which I will focus the rest of my presentation on the Mediterranean area and the soil here. The main goal of slow pyrolysis is to keep carbon in a stable form as much as possible in the solid, and pyrogas for the process is a co-product. The scope of gasification is to bring this carbon into the gas phase and to generate energy or other derived products like fuels and chemicals from this gas. So obviously, the approach is completely different. And even if I may say, the scale of the process is very different. If I produce a solid, or if I rather go for chemicals or even fuels, that is the biggest dimension you can imagine, there would be a different scale there, and there would be a different value of the product that it generates. Hydrothermal carbonization is also focusing on carbon as main product. Also, you have a lot of organic carbon and inorganic materials that remains in the water, which can origin to other uses. I do not add the hydrothermal liquefaction here because it's only focused on liquid products, on fuels. But indeed, with some lignocellulosic materials, you also have you could have a significant portion of solids also in the liquefaction, which is very challenging technologies. We do have an HTL, and it's very complicated to design and operate such kind of plants. A very major difference is the type of biochar that you generate. Carbon, as said, is the main product for slow pyrolysis in the solid. I mean, carbon in the solid for slow pyrolysis and HTC. But the slow pyrolysis option really generates a rather stable type of carbon, recalcitrant carbon, something with a very low degree of conversion. It is an amendment, I repeat, not a fertilizer, in the soil, depending on the type of soil, depending on the type of climate, but indeed it stays for long there. It is IPCC to say that, it is RED 2 implementing act to say that, and many studies. Also on the long term, we have here in the ICHAR Association, our colleagues from the National Research Council and the Agriculture Department have carried out 20 years experiments, at least on carbon in soil in wineries, for example. So there are some long-term experiments, and there's a website of the ICHAR Association collecting information on the long-term experiment. This is something that generates very different results from what are in the handbook that has been shown in the previous presentation. The slides are from the handbook from Lehman and the others. We do have for temperate climates different results now on a long-term base. So we must be careful to take this data as final one. In gasification, actually, the carbon in ash is a process inefficiency. If my main goal is to generate a gas, actually, I don't want to have carbon in the ash. And in fact, one of the methods to assess the performance of a gasifier, together with all the other measurement types, is to measure the amount of carbon in ashes. The volume in compared to pyrolysis and HTC is limited, but my interest is to have as less as possible carbon released as a product. So it's legitimate to valorize as a charcoal, as a biochar. I'm not discussing this, but we must be aware we are in a completely different business case, and our main aim is not having this carbon in the solid, or not having this as a waste, which is also a regulatory issue. In HTC, also carbon is the main element of the business model, but is a labile carbon. If you see the HTC, I would not even use, honestly, the word carbonization for HTC. I would prefer to use the term torrefaction, because actually the amount of carbon is very comparable to the original feedstock. And the type of carbon has a lot of volatiles still remained. So it's not a stable carbon. So there's a very big difference if we talk about stability in soil and generation of carbon credits. That's one key element. On the condensates, we have in HTC, we have in water organic carbon based material molecules that are there. Also, we have pyrogas that can be condensed, and it generates two different phases: an oily phase, which in slow pyrolysis is marginal in terms of volume, while in fast pyrolysis it is the major part. And then we have a large water phase rich in organic materials dissolved in water, which can be very used for various applications. This is also an area where we are carrying out research in that mode. In the gasifier, tar instead should be removed or converted. Now, one point on maturity of technology. Again, if you read reports about the economics of carbon removal and so on, there's a question mark about maturity of technology. And I think that is because they mixed up the maturity of the business and the maturity of a technology. Let me make an example. Gasification and pyrolysis can be considered mature technology. We can implement fully commercial projects on slow pyrolysis. Now, even on fast pyrolysis today, after Ensign and BTG development around 2015, 2016, same for gasification. Why you don't see this yet commercially deployed? Because there's no market condition, and this means there's not yet a clear policy addressing this. If you have a policy, if you have the right policy, I have no doubt commercial application of technology will follow, because you have the conditions. And I will come back to this now, that point. At European and international level, there are a number of policies that applies to this technology. For pyrolysis, for slow pyrolysis, emission trading scheme, CORSIA, or long-term goal for aviation offsetting, soil policies, common agricultural policies. They all belong to this area, but are very, very different between each other. On gasification, the leading policy at European level is RED 2. Now there's the proposal for RED 3 being discussed between Commission, Parliament, and Council in the trilogue. And HTC still is ETS and CAP, but still you have the problem of volatility of and liability of carbon. Respect to the feedstock, pyrolysis HTC has rather easy technologies. Of course, you need a minimum of drying for slow pyrolysis. You can process fully wet material for HTC, but apart from this, you can be rather relaxed on that point, while for gasification, depending on the reactor type, fixed bed, fluidized bed, and so on, indeed, there's a feedstock preparation issue, which is more relevant than than a multi-feedstock. If you are interested to the business case now, I will move to the use in the Mediterranean countries, so where we have most of the problems of climate. I addressed this in the conference from ICHAR last year and this year again. Exactly how to build a business case, which are the costs. Producing biochar, depending on the feedstock, can be not as much expensive. It has a cost. I can consider a figure between 200 to 400 euro per ton as a range in hot climate conditions. In northern and central European climates, it's way much easier because you have a heat demand. We don't have heat demand here. But let's start with our soil. This is our case. We have 8.5 million hectares of marginal land, which is roughly the double than what is needed to produce the entire biodiesel from rape in Europe. And that is documented on GIS basis by the European Commission, JRC, the European Environment Agency, the S2B project. And we are also warming up 20% faster than the global heating up. So the Mediterranean area is a real critical place for agriculture and for the soil. So for us, the first point is to try to mitigate the impact of the climate. I'm not saying anything new because this was already presented in the Clean Planet for All, the communication by the European Commission for DG. Well, this was from DGNR, but anyway, it was in preparation of RED 2. And the Mediterranean area has been clearly identified as the most critical for a number of effects. Not even that only, but before and after, there were other very, very serious advice from the European Court of Auditors and the European Environment Agency, which are dramatically remarking the problem of desertification, marginalization, abandonment in the Mediterranean land. The European Court of Auditors is commenting that there's no real work on land degradation, and we are not working or we are not taking sufficient measures as European Commission and European bodies to achieve land degradation neutrality by 2030. And also, I mean, we have a projected decrease in the most negative scenario by 50% by 2050 of pork, wheat, and sugar beet. Well, it means even if it then becomes 20%, it's a lot. It's really a lot. It has social, environmental, economic, and sustainability overall, I mean, climate consequence, a case like this. So we have to take action. But we have to develop long-term sustainable business model around this, this goal. And that is the real issue, how to develop a business model. These were exactly the point I touched in the conference from ICHAR last year and this year. These business models must be framed in the policy framework, and this has to be very targeted and effective. Now, this is from Luke, Finland, a long time ago. It was a nice presentation with the X-ray tomographic work. This was the first one done. There have been others from Western Ontario University, for instance, a couple of years ago that was presented in one of our biochar international conferences. And here you see the porosity. A frequent point I see in biochar to be used in soil is to carry out BET analysis, BET, which is not so interesting for us because you see that the plant available water is here, is in a range that goes from in the macropore range in that area. While BET is more interesting for other uses, for example, water and gas treatment, or carrying molecules on certain conditions for certain applications. our product is something that must absorb and release in any case, not just absorb and maintain. So if I can store water in micropores that the plant cannot take off this material, that is not of interest for agriculture. That's what I'm saying when I refer to tuning the feedstock. You can start with hardwood or softwood. That's not the same. Pyrolysis removes material, but doesn't change the physical structure of the woody or lignocellulosic material. These are woody, but then you have also the agricultural residues. Then you have the organic fraction of municipal solid waste or other organic fraction, and all this brings you to different products, also depending on reactor type. For instance, how you remove the biochar and the pyrogas, it's not the same, depending on how you do it, or the process conditions, how long you keep this in the reactor, at which temperature, and so on. Overall, the biochar structure depends on feedstock, technology, and process conditions all together. Now, in biochar and agriculture, we're not saying anything new. This has been discussed for a very long time. And these are a number of products that you can find on the market. These are mostly used on horticulture, very small applications, and things like that. But it's legitimate to ask ourselves why it is not yet at scale. What is the reason? And indeed, the reason is about cost, first of all, and then also availability of feedstock. But again, on availability of feedstock, there's a lot to say because it depends on the competing feedstock, use of the feedstock, and the policy that regulates the use of the feedstock. If you have time, next week on the 10th of November, there will be, I think it will be also broadcasted on the web. There's a meeting on soil health, and Professor Ratan Lal from the US will be present. I will also be in that panel. And we will discuss, as we did with FAO recently, about the carbon in soil issue, focusing on the area where we need. But as I said, the point is here. I mean, when I fully agree, compost, for instance, is a very valuable product in terms of environment, in terms of application. Now we'll show in a moment a couple of results and a couple of innovative uses. But the point is, if you come here and speak to the people working on waste, organic waste fraction, anaerobic digestion and management of compost or composite of this product has no value. At best, you can market this at €10 per ton. You have problems in the preparation of this product because of smell, odors, areas that is occupied. So it's a very sensitive matter. Pyrolysis can solve many of these problems and can also deliver a product. Now, what is the element that can be independent from the agronomic performances, which could be suitable for a business case, to develop a business case? Well, it cannot be the improved yield, for instance, because as it has been correctly said, it depends on a lot of factors: the soil, the type of crops, the climate, and the type of biochar, many things. So it's very complicated to say, I will have, I don't know, 10% more yield because my biochar here is producing this effect. It's very local. It depends. Even year by year, it can be very different. Last year, we had no rain 4 months. In other years, we have very different conditions here, and the performance of biochar in soil can also be very much affected by that. This is not a point that can deliver support to a business case. The only common elements to all these cases is the carbon sequestration and use. This is not a carbon capture and sequestration value chain, because this is when you sequester CO2 and you put it in a basalt cave 7 kilometers behind the floor. In our case, this is a carbon sequestration and use, because this amendment composed by biochar is used in the soil. So there's a double value. We sequester and at the same time we provide an additional benefit to the agricultural sector, or the forest, which is the use of this carbon. It's not CO2, it's carbon. So just to be very clear, my competitor in this chain is direct air capture and sequestration, DAX, in which I can have a number of advantages, starting from cost. DAX estimated costs are from IEA from 600 to 1,200 euro per ton of CO2. We are priced by much less. We can go down as 50 euro per ton CO2, 50 to 100 euro per ton CO2, which is the current price of ETS. And that is the point. If you go...
Sorry, David, we're really enjoying your presentation. However, we're just keeping track of the time. So
yeah, okay, I will speed up and try to but I know much to the conclusion. This is the ETS. Yeah, welcome. This is the ETS system. ETS is not European ETS, is a globally type of different ETS. This valorizes the carbon, and that is the element that can be used for developing the business case. I'll switch very quickly. Biochar in anaerobic digestion, what we're doing now, it can enter many places. We have already done co-compost of biochar and digestate, which has been done also in the US by USBI association. So again, it's a proven technology. This is done in Bio4A. We cultivate camelina and barley. This is the sequence of carbon in soil. I don't want to bother you with the one on top, but look at the bottom figures. This is the soil in Spain, 2 sites, no fertilization, mineral fertilization, co-composted biochar and compost only. And you see, we have more data than that, but you see, even from a visible point of view, the effect of the char in soil, and there's a publication, open access on that. And now it's 4 years, we are cultivating rotation of camelina and barley on the same soil with these 2 products, proving that we can support food production with this approach that would otherwise not be possible otherwise. So I'm going to conclude. I mean, it's a value chain. Agriculture is multi-annual, multi-products, rotation, agroforestry, catch and cover cropping. It delivers food, feed, and energy products at the same time normally. So it's one single agricultural system where this type of amendment, together with compost and fertilizer, can really provide support. My last slide is this one. We believe that business models are possible. That is mostly needed in where we have the highest impact of climate change, which is, for example, Mediterranean, Sub-Saharan African region, and other parts also in the US. We have to integrate policies because all these markets are policy driven. Otherwise, there's no way to find a compromise. ETS would be the possibility for me to implement a sustainable business model without inventing a new market. Don't forget that creating a new market for carbon will require years. It's not something you can develop quickly. And the key element for this business model is the valorization of the carbon, which is proven by many studies, carbon 14 studies, IPCC study, long-term studies we've done. But again, it has to be well done. But we have the standards for biochar. So we have a reference that we can use to evaluate if the biochar has been done right or wrong, because as any of this chain can be done in a good or in a bad way. So it's important that the bioenergy chain, and I conclude with this, are well designed and are enabler of more sustainable agriculture. This is the point, to enable more sustainable agriculture rather than to compete for them. That's all, and I thank you very much for the attention. There would be much more to say, but there's no time to do this. Thank you.
Thank you, David. That was really interesting. We'll just quickly open the floor to questions. Stephen?
I have a question about the HTC. You were mentioning the business model for HTC is product oriented. Do you know any running HTC process where a client is paying for the HTC coal? According to my knowledge, it's more waste treatment and the business model is based on the gate fees.
Fully agree with you. In fact, even if we do this kind of research, I see an issue there because you cannot, to be honest, commercialize HTC as a carbon sequestration method because you have all this labile and volatile carbon there. So it cannot be classified as a long-lived carbon sequestration, while biochar from pyrolysis can be. So the only commercial attempt which I've been in contact with in the last years were exactly conversion of wastewater sludge or other type of wastes into a carbon material, which more or less maintains this almost the same amount of carbon, and then is commercialized to coal plants in substitution of coal. But indeed, I didn't see much market to be developed in that area, to be honest.
Okay, does that answer your question?
Yes.
Great. Anyone else? Okay, David, that was really, really
You're
interesting.
welcome.
Thank you so much for taking the time to speak to us today. And if you
Thank
want
you.
to hang on, we've got another, we're going to talk about case studies and we're going to have a small discussion at the end if you want to stick around.
I will see. I will stay connected. I don't know if I can be online. Okay. Thank you.
All right.
Bye-bye.
Okay. Now, just very quickly, we'll hear from Stephen. He's going, or should we do that after the break?
After the break.
Okay. So we're just going to have a quick,
short introduction to the session.
So Stephen's going to introduce the section, the last section, which, as I said, is talking about case studies. So please help yourself to tea and coffee, and we will resume at 4 p.m. So that's 8 minutes. Hello and welcome back to the last session. I hope we still have our guests online, and oh, there's a funny light on the camera. We can adjust the still. We look like we have halo. Are we able to turn up the front one, or we have to turn them all?
I don't think.
It's okay. It's better with the lights on for us here because it's getting dark now. So excuse us online if it's a strange halo effect, but you should be listening to our voices anyway. Now, just welcome you for the last session. So we're going to talk about the case studies, and Stephen's just going to give us a little bridge from the market to the case studies, and then we'll hear from Paul going to start introducing the real case studies. So over to you, Stephen. I'll share your screen to do it, your presentation. Why not? Yes. Okay.
Okay. Just very, very fast ride through the SNG, the main product in our project. And what we think SNG has to be considered on a larger scale. It's not only SNG from or methane from woody biomass, it's also, as we heard several times this morning, biomethane from bio-waste and agricultural biomass. And there is no real competition. just maybe for straw as a feedstock. But on the other side, we need both to decarbonize our European or global gas system. But there are also some other technologies. That's on the one hand, methanation of CO2 with low carbon with hydrogen from low carbon electricity. And what we can do, or what we are doing with natural gas at the moment, is we use it for power, heat, and for the transport sector. For the transport, we can also use the hydrogen directly, or maybe more efficient to go for electric vehicles, at least for some of them. For methane, SNG, we see LNG and CNG as a market, but for a special niche market in the transport sector, mainly heavy trucks or agricultural machines. It will be difficult to run agricultural machine with the weight of a battery, because after several times your soil is flat. Okay, one idea is also we inject SNG into the grid. The problem is each country has at the moment its own grid injection restrictions. That's sometimes really different about the, for example, the CO2 content in Germany can be up to 10. In Italy, for example, below 3%. And if you go through this, you will find a lot of differences. Also, the heating values are different. It's somehow because in Germany and in France, you have the Dutch low calorific natural gas, and in some regions also the higher energetic natural gas. And what we have to do in the frame of this project, because we see there is no one SNG grid injection requirements, we have to do it for each country. And that's why we are going for case studies, and we have to do it really case by case. There's another restriction if we consider our SNG as CNG. The hydrogen content should be lower and compared to the natural gas grid. We had a discussion some minutes ago. And this is under review. There are some harmonization, standardization developments. On the other side, the whole gas grid in Europe is more or less also under pressure for the assumed increasing amount of hydrogen entering the grid. So the gas grid and the grid injection requirements are under construction because of the increasing amount of hydrogen. And in this situation, there is also the idea to integrate SNG or biomethane, which has slightly different compositions and impurities, to retrofit it. Again, one reason why we should target case studies. A short view on the economics. I think we are all aware about the gas prices in the last 15 months. And what we see here are the prices for natural gas on the stock market in Leipzig for the next 3 years. At the moment, we are on a quite low level compared to the next year. And for the years later, we expect again. Interesting is, in former times, 1.5 years ago, the gas price was around 60 euros per megawatt. At the moment, we are between 100 and 150. If we compare it with literature values for the SNG production costs, we are not so far to estimate our costs, but we assume we are at least in the same range. Then we see with the current natural gas prices, it seems to be economic competitive. That's something we will check in the case studies. Of course, wood has or the biomass price has an influence on the SNG price. The effects on the wood prices of the high gas prices, we have to see At the moment, they are going up. On the mid to long term, I expect the wood price will go down. But yeah, again, there is no one solution. We have to split it into case studies. And if you have a look on the gas market for SNG and or all green gases, the only green gas at the moment at the market is biomethane. There is nearly no SNG grid injection, as well as for power to gas option. Germany, some plants are running. What will happen in the future is another option. But what's obvious is the biomethane is consumed depending on incentives and yeah, some history in the different countries on the gas market, completely different. In Germany, most part of the biomethane is going for power production for incentive reasons, and in Italy, it's completely different. The biomethane is going completely to the transport sector. That's because in Italy, there is a longer tradition of having cars on running on gas. And in other countries, it's again different. In the UK, for example, gas is used for heating of individual housings and for industry. That's completely different. Again, for the case studies, we need a case-to-case investigation. So that short sum up, SNG is one future puzzle piece for green gases and for greening our gas system. The regulation for grid injection is very diverse and dynamic due to the H2 readiness developments, and it's under retrofitting. The increase of the natural gas prices at the current situation, and if we took the at the moment discussed LNG import prices to Europe as a benchmark, it looks like if the biomass is not increased so far, at least SNG from biomass or from gasification is likely competitive with LNG imports. Not from the amount, but just from the cost point. And where we see a future market for SNG, we already heard it or 2 hours ago, it's transport. Some sectors of the transport sector you can't electrify. That's for sure. For the maritime sector, it will be hard to drive a huge ship with a battery or electricity with a cable. So LNG will be likely one solution for defossilization of the maritime sector. And the same for some cars. LNG or CNG will be an option in regions where it's quite expensive to install electric charging infrastructure. For example, northern Sweden, northern Finland, some rural areas. It will be quite costly to install the infrastructure. So in this region and for some special sectors, there will be a market for green fuels, and gas is one option of this. And industry for some for high temperature processes, electrification is not an option. So for some processes for glass production, for example, you need high temperatures and therefore you need a fuel. And gas is the obvious one, and green gases should be the future. That's it. And now I hand over to Paul, who will explain more in detail our case studies we want to investigate. I think the reason why we choose case studies is obvious.
Thank you, Stephen. So now
Questions for Stephen?
there are no questions online, but please, anyone on the floor, in the room?
I was thinking too fast.
He didn't want to answer any questions, so let him go.
No, if you have questions, ask.
Yeah,
That's why we are here.
otherwise, we can, for this session, perhaps they can all come in the discussion section if you think of anything later. Okay, not too later, because not too much later.
If not, I will be the last one who leaves the room, so there will be enough time afterwards.
Stephen will be here cleaning. Okay, so over to you, Paul. Please come on up. And, please take your standing
official place. Okay.
magic X.
And I'll start by saying thank you to Stephan and Marie-Laure and Emma and everyone for organizing a really interesting day. It's really great when the FlexSNG team gets together.
Just sharing the screen here. Okay. Sorry. No. There we go. That's right. So it can go.
There we go.
There we go.
So my name's Paul Stewart, and I'm a professor at Polytechnic in Montreal, and the other university involved in the Canadian part of the project is Université Laval, and we're looking at systems engineering. So we haven't got any ideas, but we analyze all the great ideas of the people in the project, and we're really thrilled to be part of this H2020 project. So a couple of discussion points. The first one is about industrial symbiosis. That's one of the key areas that we're looking at using systems. And it's very important, obviously, in a commodity strategy where we make bio-SNG and we make biochar. And just to introduce one of the case studies, the Canadian case study, and then I'll pass the baton over to Kostas and Christina, who are anxiously awaiting us in Greece to continue with the rest of the case studies. So industrial symbiosis, we all who have done techno-economics know that we need a low feedstock price. We need to sell the product for as much as we can, and selling the product for as much as we can, wars notwithstanding, relies on policy to a great extent. The biochar has got a lot of uncertainty about it. We won't go there. And of course, then there's the capital cost. So what is missing out of that really is how it fits into the background, how it fits into, is it closer to natural gas pipeline? Does it have hydrogen nearby? And things like that. Can it energy integrate with its environment? And that's industrial symbiosis made simple. So going a little bit further with it as a definition. So the question is, with Kallenberg in Denmark is the most famous example, of course, where you have an industrial park and you have that interaction. But now going into the 21st century, we're looking at it more broadly. We're looking at sharing data and digitalization. We're looking across the value chain, if we will, and so how we can collaborate in all ways in order to become more cost effective. So industrial symbiosis in some broad way then lets us lower costs mainly to increase profitability and competitiveness. And at the same time, whenever you get more efficient, you become more environmentally preferred, more GHG reductions and things like that. And so that's a byproduct. So somebody named Georgiadou, she's the queen of industrial symbiosis. She wrote the book. She's the pioneer in the area. So she talked about, of course, type 1, which is exchange between facilities. And so we take a waste from one facility, we might modify it to improve its quality, and it can become a feedstock in the facility nearby, or maybe we share wastewater treatment plants. So that's historically, that's been sort of the definition. So now we're going a bit further. So within the facility are firms, so that goes to other sites, perhaps in the facility and the firm, and creative works in the area of collaboration, and that is an industrial symbiosis form. So between firms co-located in an industrial park, and things also that are distributed over geography. So a biohub transporting that, or a hub and spoke model, as we talk about, where we pre-process biomass over here, then we ship it to a central processing facility. And then the virtual connectivity between organizations where we want to share data and eventually stream data in order to be able to make decisions as to where our trucks go and how we share materials, mass and energy balance. So now it's got complicated, hasn't it? Because we will go beyond the local environment and we consider this value chain perspective. And so this is more of a 21st century view from a systems engineer perspective. This comes from François Maréchal at EPFL. And so in the middle, you've got the idea of industry facilities across sectors. And the people who succeed in the bioeconomy anyways are largely going to traverse sectors. And here, around here are the analytics we need to quantify industrial symbiosis. And so we're beginning to look at that now systematically with those different dimensions that we talked about last slide, and look at what analytics are needed to be able to optimize, come up with practical models of industrial symbiosis for something like FlexSNG. And so to optimize resources, energy, and capital. So one more very interesting part here is that we're looking at FlexSNG with two modes of operation. This shows three, but the idea that we'll go from one to another different parts of the year, and each one will have a different potential for industrial symbiosis, obviously. So that's the end of that part, and then I'll put the two together. This part here talks about the Canadian case study. So it's a company called Greenfield Global, and the site is Varienne. It's on the south shore of Montreal. And so Greenfield Global, it's a private company. That means they don't have that much capital to spend $1 billion on a world-class biofuels plant. But they do have hundreds of millions of dollars, so they'll make a consortium if they go down a path like this. And they're a leading producer and supplier of high-value, mission-critical raw materials, ingredients, and additives necessary for the low-carbon economy. And they're really one of the Canadian, if not the Canadian leader. And this is their Varennes site. So it is a bioenergy site. Here at the heart of it, they've got a corn to ethanol plant. Over here is a Praxair plant, and they recover the CO2 from the fermentation and clean it up and send it over. And over here we have an anaerobic digestion plant, and they're gathering a lot of the regional landfill waste and bringing it there and making bio-SNG. So they've got a plan, and these are the three main components of the plan leading to the late 2020s. This part here is to expand significantly their corn to ethanol. This part is to use electricity. We have green electricity and in Quebec hydro to make green hydrogen and oxygen. And this is to double, this project is actually started to double the capacity of the biomethane anaerobic digestion. And so we're going to look at that with a 2029 perspective as a startup date for a FlexSNG, hypothetical FlexSNG plant. Let's get going and do it. And then talk about how it can best fit in. So where we use hydrogen, where we don't use hydrogen, but also these other forms of industrial symbiosis. And this good-looking guy, I don't know if he's one of the participants. He's a PhD student who started a bit over a year ago now, Francis, and he's actually going to defend his PhD proposal soon. And so we've developed a preliminary framework. It's going to change for sure as he executes, but it's based on atomic targeting, and then it's based on a scenario analysis and looking at symbiosis, different forms of symbiosis in different scenarios after we've done the atomic targeting to optimize the use of hydrogen and the other chemicals that are implicated by the bioenergy site and its future site. We're also looking in this case study, in this one particular case study. So obviously it's in Canada, there's forest wastes and a big volume of forest wastes as in much of the country. Here they're playing in the sandbox of corn to ethanol. So there's ag waste that they can, clearly they've got pre-identified relationships that they might build on. And then there's the municipal side. So, you know, they can do a better job of picking up more of the municipal wastes that they're already entered into. And Montreal, they're on the south of Montreal regional, but Montreal hasn't really done anything good. So there's a good potential for the wastes. And so we're going to look at a number of those combinations for the one case study. So we'll have
if you will, some heuristics, I hope anyways, on industrial symbiosis and different configurations. Was I too long?
No, you were perfect. I was laughing that Montreal hasn't done anything good. Yes.
You can do better.
Yes.
That's potential.
Okay, thanks, Paul. So we'll just for this section, we'll wait until after the Kostas and Christina have spoken, and then we'll have all the discussion and questions together. So now over to Greece. I'll stop sharing my screen. And Christina, Kostas. Hello.
Hello to all of you.
Hello.
Hi, Kostas.
I'll share my screen.
Yes, please do. Okay. So
can you see it?
Not yet. Yes, you can now. If you put it into presentation mode.
No.
We can see your.
What's this?
It's a common problem today.
I don't know why.
Yeah, we didn't know why either.
Switch. Okay. No.
Oh, yes, perfect. Yeah, well done.
Thank you. I'll start, and then Kostas probably would like to add something. So hello to all of you. I'm. Can you listen to me or no?
Yes,
okay, I think that my internet connection is not great today. That's why I asked you. Sorry, can you listen to me, right? So I'm from CERT, Center for Research and Technology in Greece, and I'm part of the FlexSNG team. Okay, I cannot change. Oh, sorry. I will try to briefly show you the case studies for the FlexSNG project as they are currently defined. Probably in the next steps of the project implementation, minor differences will be made. The objectives of the determination of the case study were actually many. Geographical locations from different parts of Europe, northern, central, and southern, and the implementation potential of the FlexSNG on them have been analyzed. This analysis in the context of regional characteristics. That means that feedstocks availability, energy, market characteristics, existing natural gas infrastructure, potential biochar uses, and general regional heat demands are data that have been taken into consideration. Moreover, possible synergies between different energy carriers, such as biomethane, biochar, heat and electricity, and also energy conversion chains and industrial symbiosis have been taken into account. Another clear target is to verify the improvement of the environmental performance of the FlexSNG concept comparing to other technologies. And of course, the evaluation of the business potential of the project and the advantages that could have over competing technologies is a key factor of the case study definition procedure. So to sum up, the case study's potential is based on techno-economic, socio-economic, and environmental point of view. And I should also mention that all the case studies were initially defined after the previous consortium meeting, and that a common benchmarking framework for the techno-economic assessment is currently being developed. One of the key benefits of the process is the feedstock. Considering that biomass availability is highly country or even region specific and also has an important seasonal variation, we believe that the wide feedstock potential improves the FlexSNG implementation. Also, Paul talked before for the different FlexSNG plant concept. It can be tailored for both rural conditions to process a variety of biomass residues available from forestry, forest industry, or agriculture. And this is the biorefinery FlexSNG plant. It can be tailored also for urban environments where the feedstock is actually waste-derived materials, and this is the city refinery plant. And the synthesis process can also be coupled with electrolysis, and this is the hybrid plant that actually can increase the biomethane output and by the hydrogen boosting. I'll start with the brief presentation of the FlexSNG case studies. Starting from the Northern Europe, case studies are located in Finland and in Sweden. A city refinery plant will be located in Helsinki, in Helen site, where two parallel gasifiers will operate with SRF and demolition wood and urban waste wood respectively. The final end products of this process will be SNG and biochar. SNG will be used for regional heavy-duty road transport and for district heating needs, while biochar will be used for urban soil management. The other potential city refinery plant in Helsinki, in Lahti site, will use a mixture of industrial, commercial, and building site waste to combine heat and power production. And the biorefinery plant in Sweden, in Vero location, will use woody residues from pulp mill in order to produce SNG and biochar that will both be sold in external markets. To continue with the Central Europe, here are also three potential case studies. One hybrid plant will take place close to Hamburg in a region where there are wind parks. Agricultural residues, solid minor waste wood, and other possibly imported biomass will be used to produce the SNG and biochar. The first one will replace the Dutch natural gas, while the second will go for urban soil amendment. In France, in Fibre Excellence, will be a biorefinery plant that will use woody and agricultural residues. Final end products will be SNG and biochar. And the city refinery plant in Corse Island will operate with woody residues from pulp mill, and its final products will go as a CNG for power and transport needs and as high calorific stored fuel biochar. And for the end, the case studies of the South Europe. A city refinery plant will be in Crete Island and will operate primarily with RDF and secondly with agricultural residues such as olive kernels and prunings. The final product application will be CNG for power and transport needs for public buses and trucks. And the biochar will be used as a fuel also. The other Greek case, which type is not decided yet, will use municipal solid waste and agricultural residues, and the produced SNG will be injected in the natural gas grid. That's all for me and the European case studies. I don't know if Kostis wants to add something.
Yes, thank you, Christina. Just a short comment on that is that the FlexSNG concept offers the opportunity to examine the different case studies with completely different aspects in terms of the feedstock use, in terms of the final use, and last but not least on the scale of the size that has been selected for different cases. This is, of course, a very challenging issue that we are going to address in the following months, and we will also be happy to come back again with results from this business studies in the forthcoming next workshop. And another also important aspect is that this analysis will not only focus on one criteria like the economic viability, but we aim to develop a multi-criterial analysis taking into account all these aspects from economic, environmental point of view, taking them into in one assessment for the case studies evaluation. Thank you. That's from my side, and I will be also happy to contribute to the discussion afterwards.
Thank you, Christina Costas. That was really nice. Very concise summary of what you're looking at there. And now we're over to discussion. So we'll welcome back Paul to the floor, and just a few slides to share here to give him a nice backdrop.
Thank you, Emma. And so I'm exhausted. I'm ready to have a beer. We've covered a lot today. That's for sure. So, but this is kind of the best part of the day. Let's go through it one more time. So here we have it, FlexSNG process. It's a great idea. We started off by looking, BTT looked at it as a whole and its modes of operation and where the innovation was inside of it. Then creative optimization stepped in and talked about the innovative ways that they're going to choose some case studies and focus on how we reduce significantly the cost model and then optimize the costs for biomass delivery to FlexSNG. Then Sumitomo went through the syngas production, gasification in the syngas island, and how they can deliver that as one of the most credible companies globally to be able to do that. Then Wood stepped in and talked about a technology that is proven, that is unique in the way it's a single pass, temperature controlled with steam and CO2 to achieve that, and a robust catalyst. And then we had a whole bunch of discussions and very interesting debate on, first of all, the policy framework, then a world of possible applications on the biochar, and then briefly at the end, thank you, Stephan, on the key product, the bio-SNG. So we really covered a lot of turf from the beginning of the day to the end of the day, and then we said, well, let's not forget the case studies in industrial symbiosis that could come from that. It's all covered. I would say in terms of developing a new process going from TRL 3 to 5. I think it might be a bit further than that when it's all said and done, but it's really an exciting project. So here, we'd like to open the floor. So everybody's been thinking about it all day, and we're engineers and scientists, so we're a bit cynical. And so maybe we could go around and people on the FlexSNG team and people who aren't on the FlexSNG team, what do you think is the main strength of this process? What do you think is the main weakness or concern that you might have? And it's okay. Or what is your main take-home message, right? What are you going to take? I don't know how much notes I took today, but I have just tons of things I learned because of the breadth of the discussion, and we all see it in our own way. So, what is your take-home message when you go back home? So, or whatever you want to talk about, if you don't want to talk about those things. So do we have any volunteers, or should I just start picking on you and embarrassing you on the spot?
The professor's coming out.
There we go. I'm going to walk around now. Somebody want to start off? And this goes also for those of you who are virtually participating, of course. Yeah, thank you.
Maybe I start.
Yeah. So introduce yourself and your company would be great.
My name is Henry Steinweg. I'm from the university in Karlsruhe. I'm not part of the consortium. So I'm a visitor, so to say. I'm a PhD student. My first year, or my first year is finished right now. And my field is process development for CCU processes with syngas as feedstock, fermentations to be precise. So not biochar, not gasification, but somehow comparable. And for me, it is really interesting to see that the process concept includes this flexibility of using this seasonal availability of feedstocks and switching from focus on biochar to SNG. And I'm really curious to learn maybe over the next 18 months in your project how this switch is realized. So that's maybe the most interesting thing and the most curious thing for me at the same time. What do you think? How can you manage this transition?
Well, certainly we'll pass that over to Ilka and Sanna, but there's a story about that. In my case, when I first saw Tuomi, I'm a consulting engineer, and so we talk about capital utilization, and to have two modes of operation, you're wasting capital because one of them is going to be, and it's a capital intensive process. But as it turns out, and this is just for clarity, because it wasn't obvious to me, it's working at 100% capacity under both modes of operation. So it took me a while to work that out, so there's no waste of capital, if you will. It's just different ways of using the capital. And certainly digitalization will play a big role in going from one mode to another in how it works. But also, if it's really flexible on the other side with the biomass there too, that, you know, there'll be a set of KPIs, but it's not obvious to, variability is the enemy of large continuous processes, if you know well, I think. Ilka or Sanna, do you have comments on the two modes of operation, where it came from?
Well, of course, like we always need to look for something new in these projects to be developed. So that's also one honest comment for that. But then about this, in a way, the strength of this process, it comes from the ability to use wide variety of the biomass quantities and qualities, and that way we hopefully in later stage see that then we can get the feedstock cost at a reasonable level. Because I think if we look at these kind of processes, the end product price comes mainly from the capital investment and from the raw material cost. And those are the dominating ones. And of course, we need to tackle those both to get the capital costs lower, which Sanna mentioned in the beginning of this day.
Yeah.
And then get the biomass or feedstock cost as low as possible with all these means and the flexibility of this process.
There you have it. Flexibility is, and it is the key, I think, to large commodity processes. We have another question in the back in the middle.
Yes, I am Fabio. I'm PhD student from the University of Applied Science in Switzerland. So I think for the project, the main strength was the fully generation. We produce a lot of products like biochar, heat, and methane. But we didn't have a lot of details about the technology, but I think like for the technical challenges, because there is a lot of process and steps during the production of to go from biomass to biochar to syngas, especially for dealing with the biomass with high ash content. Yeah, I think that the fluid speed or it's adapted to this kind of biomass, but for there's also a challenge for about the gas property, the syngas we produce. So you have to clean it in terms of tar content. I don't have an idea about the tar contacts by the end of the production, but there is a step of cleaning up this gas. But for the economic, environmental aspect of this step of gas upgrading. So
So we'll give you a beer, and Ilka Bear will lock you in a room for a few days. I think. Do you want to? Yeah, no, those are big concerns.
The upgrading and dealing with the biomass with high ash content. So there is a lot of challenges. So I don't think for FlexSNG how you deal with these challenges.
Yeah, well, I can briefly discuss now about this decision. Of course, now the one thing why it was not today that much discussed that we will have the validation runs with our pilot unit then during the next 12 months or so, and then we have more to report on that side. Well, on basic side, this where this fluidized gasification has been already applied is like this high ash content biomasses as bark, for example. And then now when moving to more like agro biomasses, then it becomes a bit more challenging.
Yeah.
But there are ways to tackle it. It might then lead to bit lower conversions because we need to avoid sintering and these type of things. But it can be then also bed material additives which can tackle part of that.
Sorry. You have to face this way when you talk. He's not being impolite. He's just.
Yeah. And then about the gas purification, there is about the tars. They are partly tackled already in the gasification step. So the temperature levels and then bed materials are kept set. We partly decompose tars there, and then the catalytic reformer is then tackling those major part of that. So we decompose the tars, and at the inlet or at the outlet of the reformer, there is we can reach based on now data which we already have and the runs we have made about 200 to 300 pp, so milligrams per cubic meter of benzene. Higher components there are hardly not any. So that's like the level which we can reach. So and that's fits quite nicely with the level which then Vestas tolerates.
That's good. At least that's a starter. You could still have that long. And you know, I'm going to throw it into it. The weakness I see, and that's because I work with a lot of companies, is almost for sure that companies will go with one product and it'll be bio-SNG, and they're going to consume the biochar, because the discussion we had about the biochar, both sides are right and both sides are wrong in that discussion, if you will. But it's enough to scare off any company not to go down the path of trying to sell an ambiguous value proposal for something called biochar. That alone would kill it. So normally a company will just make that one product, stick it in the pipeline, that's their core business, and then maybe start to tap off the biochar. But the difference, the other thing that seems very complex with that is different feedstocks are going to give you different biochars, and I think vastly different biochars that'll have different value proposals on different soils with different pHs, with different crops and rotations, and so that value proposal just it's going to be a hard one to sell, I would say.
Maybe one comment to that is, of course, that as you're speaking about the industrial symbiosis, so maybe in that way, one side product as biochar can be then others like a business. So it's, of course, from that point of view, we can maybe find like optimal business concept.
Yes, and with joint ventures, and that is a model in Finland, actually, the bioproducts mill. This big company, Metsä, builds a big, beautiful pulp machine, and then brings, with all the byproducts, brings around small and medium companies with innovations. And that anchor firm hosts, you know, the legal requirements, the cost requirements, they invest in some of them, but they take care of the people around the periphery with the byproducts. So the more money they make, the more money they make. And it's a very good model. So that's a great point. Yeah. More comments before I pick on people.
I think I have a comment. It's a positive thing and perhaps a challenge. It's more of the EU legislation level here, because we notice that there's a positive feeling that we want to produce more, but we also know there's legislation that could limit the use of biomass. For example, it's very different when we can see it in geographical countries. That, for example, what would happen if you limit biomass in Sweden and Finland? How would that affect the overall decision to do these kind of investments as well? Because there's a danger here that if you go into this producing more gasification with biomass from especially forests, there's a danger you might not be able to do it in the future, and there has to be sort of a backup feedstock. And I think that's, looking at the presentation from earlier, potential. There's a lot of potential, but do they all work in the, like, in a common sense? Can we create recipes that can make these co-handle? That's my take from it. It's both positive and negative, I guess.
Yeah. Comments on broadly on the policies thing in Europe. As a Canadian, I find it a little crazy, confusing. NGOs, bless them, but they're very strong. And the fundamental of the argument that it seems is in Europe is if you cut down a tree, you have a carbon debt, because the carbon is no longer there. It's going to get used for something. Well, we're using it in a sequestered manner. Another tree is growing, and it's the slope, it's the rate at which we're consuming carbon in the forests that are growing. The younger forests, as Erik will tell you, as we breathe and eat more when we're young and much less when we're old, and we still get fat. Trees are the same. And so we want to manage our forests, not cut them. So everyone go home and cut down a tree and plant a new one. And you're doing the best thing for the long term. But that is a strange argument from that side of the ocean about the policy debate that you're having in Europe.
We still have Maria online. I don't know if there's anything you want to add about policy in Europe. Perhaps she's just there in name.
Maybe one comment from my side. I fully agree. From the Canadian perspective, it's amazing. But another Horizon 2020 project that's dealing with biomethane, and they are developing a mechanism with some guarantees of origin, so that the provider in each country can guarantee the bio origin of the biomethane, and then it's tradable between the frontiers. So then it's a tradable good. So for example, in Germany, someone wants green gas for some reason, and the biomass is in Sweden or Finland. It would be interesting if someone invests in Sweden in SNG production, feed it into the grid, and gets the, we named it yesterday, market premium market.
Mm-hmm.
And maybe someone in Germany is easier to refinance this market premium price on SNG if it's just produced somewhere else where the biomass is.
And you're transporting.
But biomethane, if I understand this project right, it's going into this direction.
That's
And
great.
for biomethane, there is a huge production.
And agree. Yes.
Is there an advantage for the CO2 in the atmosphere? You are allowing another person to emit more CO2 when buying to lower cost when buying renewable gas.
I'm just looking on someone who is willing to pay an additional price for CO2 emissions. Somewhere the money has to come, somewhere has to pay. Defossilization of the energy system will likely lead to higher prices. Biomass is a scarce resource and it's maybe the most expensive renewable energy. But I'm quite sure that a certain part of the society is willing to pay higher prices. Not everyone, but the idea is, or my vision is to find someone who is willing to pay money for defossilization of the energy system. Not everybody is able to pay higher prices or to spend money. Someone refused. But I think there's a growing share in the population. And if I look at the Fridays for Future, I think the younger the people are, the more motivated they are, because the more urgent is the problem.
And there's a precedence for it on the electrical grid. In deregulated environments in Canada, the individual is allowed to pay for green electrons. We don't know what color they really are, but they're allowed to pay a premium for green electrons on their utility bill.
But other people will buy more fossil electrons.
No, in
If you
parallel,
don't decrease the amount of CO2 certificates. If you don't reduce the amount of CO2 certificates, this will mean that other people will.
But it's a political decision. If you have which amount of CO2 certificates, or if you go for a CO2 price with an increase, it's a political decision.
But if you buy renewable protons or electrons, then you will more certificates are in the market. More free certificates will be in the market.
We're going to let you have the last word on that. And another question.
Well, we had Maria, I think.
Great.
Popped up. I would like to hear the EU level on the legislation.
Hi, Maria. Sorry, you popped up and then hopefully you're back with us. Perhaps there's a delay with the.
Or she's on the phone.
Yeah.
At a moment.
We've had a second. If you are there, we'd really like to hear from you about some EU policy.
If you can write to her, perhaps we can go on with other questions.
Yeah, she is.
Hi, Maria. Thank you.
I don't hear you very well. I don't know. There's a lot of echo when you talk, so I cannot really follow very well your conversation. So what would you like to know about the EU policy?
I'll let the EU people phrase it.
Can you hear me well?
Yes.
We were wondering how it works with having legislation that we want to increase the use of biomethane and we want to keep on building it, but we want at the same time to limit the use of especially biomass and forest residue in the Scandinavian countries, for example. How does that, what's the talk and what's the idea and what's the strategy going forward?
To reconcile those two things.
Okay, I understand the worry about limiting biomass for heat and power, because the discussions now in the trilogue and parliament basically are about heat and power. On the other hand, biomethane is very much politically supported That's why it is part of the Repower EU with a big target. And all over the biomethane action plan, which I presented this morning, there is the word sustainable. So the way is to increase the production using sustainable feedstock resources. This could be the residues and waste, even residues and waste from woody biomass. It is not excluded, but they have to obey to the sustainability criteria that were proposed in the recast of the RED II. So yes, there is a concern of not utilizing primary wood for biomass-based heat and power generation. And this is where all the constraints go. But for biomethane, there is no such a constraint as long as the feedstock is sustainable.
So that's interesting. It's a political answer. To be fair, it's a political answer.
Yes, it's political.
Sustainable or it's not. It's interesting.
I'm explaining to you what is now the discussions, and not even this request from the parliament to have a ban on the use of biomass, primary woody biomass for heat and power. It is still in discussion. It is not adopted. So this is a decision taken in the parliament, but not yet adopted by the council, with the council and the commission. So yes, there are many concerns on the use of biomass for heat and power. This is true. But on the other hand, there is obvious political will for biomethane.
You have the answer.
I have my answer.
Thank you, Maria. That was an interesting answer, actually. Yeah.
But it makes sense to some extent.
Explain. That's okay. We'll give you the last word on this one. Why does it make sense?
Yeah.
It's interesting.
Yeah, good. Yeah.
I'm not involved in these discussions, but for wood, to use wood in construction or where else means that the CO2, this C of CO2, is stored for a very long time in a building. Yeah, and this will not come back to the atmosphere. And this is not true for the residue after the construction. Then you have the wood, and probably you are not able to reuse some of them or all of them.
You mean once the wood from the construction becomes demolition wood?
Yes.
Okay.
And then
but it's part of the same life cycle.
Yes, but
okay.
You have a cascade.
Mm-hmm.
A cascade, then first you use it for construction or other purposes, and after 50 or 100 years, you will keep the CO2 for 50 or 100 or 20 years safe, and then you will have the final use of electricity or energy. And for biomass from agriculture, we are also searching for cascade uses.
But you can't have one that is life cycle design, and circular economy is about designing at time zero through to the end of life. And so you can't say, well, we want to build houses with wood, but we don't want to ever demolish them. If you build the house, one day you'll demolish the house.
I don't expect
a great use of wood is to build a house because it's long-lived carbon.
Mm-hmm.
And then now you're going to tear down the house, it's its end of life. So now the question is, what do we do with that wood out of all of the possible options we have? And to me, it would seem logical that at the time zero, when we build the house, we look at it as going into a biofuel or into bioenergy. But you would distinguish between it being biofuel or bioenergy when we build the house or before we build the house.
Yeah, but
we'll drop it there.
Okay, thanks for that really great discussion, everybody, and participants online, and Maria for joining us again. And It's been a really great day, and just to round off with some concluding remarks is Ilkka back again for just to say thank you for coming.
That's I think Paul nicely already showed what a day. So there has been, I think, really nicely covering in a way the process which we are developing, the industry there, and now also the policy part and the markets. So quite well covering, and of course then what I need to remember. So thank you for each of you who came here, each of you being online, and especially those who have arranging this. So thank you, and
thank you, and bye-bye.
Yes. And so thank you for this, and have a nice evening and safe trip back to home.
Thank you. Bye-bye.
Thank you, everyone. Thank you very much. You are free.
Thank you.
Bye.
Thank you. Thanks, David. Thanks, Sanna.